This video today is a crash course on data structures from scratch in Python. We're going to implement multiple different data structures from scratch in Python to learn how they work, to understand them from the ground up. We're going to start with linked lists. We're going to then move on to stacks, queues, hash maps, binary search trees, heaps, tries, and we're going to finish off with graphs. The goal here is not to build these data structures so that you can use them in your programs. The goal is to understand them by building them from the ground up. Now, this video is a compilation of 8 separate videos that were already uploaded to the channel, but you guys always prefer these all-in-one videos. You prefer to have everything in one place. So don't be confused if in the videos I'm talking about in the next episode, in the previous episode, I'm referring to just earlier or later in the video. Now, if you get value from this video, let me know by hitting the like button, subscribing, and leaving a comment in the comment section down below. But now, let us get right into it. Alright, so we're going to start off this tutorial series by implementing a linked list and a doubly linked list in Python today. Now, as I already mentioned, the goal of this tutorial series is to understand the data structures and also the runtime complexities of the operations that we perform on these data structures by implementing them from scratch. So we're not going to use any packages, we're not going to import any data structures, we're going to build them from scratch in Python using classes. Now, I'm going to always briefly explain the data structures so that you know what it is about in theory before we implement it. But if you want to have a more detailed explanation, I have a tutorial series or a course, you could say, on algorithms and data structures. There you can find more details about them. But I'm going to give you a brief sketch of the basic data structure every time before we start coding it. So let us get started briefly here with the linked list. I'm going to sketch it out. It's quite simple. The basic idea of a linked list is that we have so-called nodes. So we have, for example, let's say this is a node, and this node has a value, for example, the number 10. Now this node also has a pointer or a reference to another node, to the next node, so to say. And this node then again also could have a value, 20, and it points to another node, and so on and so forth. They can have different values, and at some point some node will have a pointer to none. In Python it is none, in other languages it's a null pointer, whatever. It's basically the end of the list. So a linked list works like this. You have nodes, and one node points to the next node, this node points to another node, and so on until we get to the end of the chain, until we get to the end of the linked list. And this structure, of course, means that we have to perform different operations in different ways. For example, if I want to see if a certain value is part of the list, I cannot just jump to that value. I have to go through all the values. So in order to see if 30 is part of the list, I cannot just look at the list and see it. I have to say, okay, let's go to the first node. Is it 30? No. Jump to the next node. Is it 30? No. Jump to the next node. Is it 30? Yes, I have 30 in the list. And because of that, of course, this is going to have a runtime complexity, which is in O of n, linear. By the way, if you don't know anything about runtime complexity, I would recommend that you watch some video. You can watch my video or another video that explains the basic idea of runtime complexity, because I don't want to go into too much detail here on the theory in this tutorial series. But the basic idea is how many steps you need to perform, how the complexity of your algorithm increases when you increase the input size. So in this case, the list has n elements, so 3 elements. And in the worst case, I have to go through all 3 elements to find the element I'm looking for. Because of that, we have a runtime complexity of O of n, a worst case complexity. That's the basic idea. So that's a linked list. A doubly linked list is the same thing, just that we have 2 pointers. So every node also points to the previous node. So it's basically like this. And then here we have a none pointer, or none reference again. So it's just it's just in both directions, and this of course makes it easier to prepend or to do certain things, and that's just the difference here. So we have 2 references. We have going into both directions. That's a doubly linked list, and if it's just going into a single direction, we have a normal linked list. And this is what we're going to implement in Python, and we're going to also implement a bunch of different operations. So for example, I have my code prepared here. We're going to traverse it, we're going to display it, we're going to see if it contains some values, we're going to calculate the length, or we're going to get the length, we're going to append, we're going to prepend, we're going to insert at a specific position, we're going to delete, we're going to pop a specific index, so remove an element not by value, but by position. We're going to get, and yeah, that's actually it for the linked list. So let us get started now with a new Python file. I'm going to call this linked list py. And we're going to start with the most important class here, which is the node itself. So we're going to create a class node, and this class node is very simple. It's just a simple constructor and a init method where we say we want to have a value. And every node is going to be initialized with a value and a reference to another node. So we're going to say here self.value is going to be equal to the value, and self.next in the beginning is going to be none. So every node when we create it is not going to have a next node. That's all a node is, a value and a pointer to a next node, but by default this is going to be empty. It's going to be none. Now that is the node. The linked list is then another class which utilizes the node class. So we're going to say now class linked list. And we're going to say that when we initialize a linked list for the first time, we're going to set, we're going to initialize the head node. So a linked list has a head node, which is the beginning node. We're going to just take this and set it to none in the beginning, because if the list is empty, we don't have any nodes in there, so we have none. But once we add a node to the list, the head node is going to be that first node, and every other node is going to come afterwards, unless of course we prepend or insert. So we're going to say here self head equals none, and that is actually all we need. We need the head of the list, and then we can perform everything from the head onwards. Now what we're going to do now first here, before I go into the other functions, even though I'm going to implement a couple of functions. Maybe before we start with the implementation, a good idea would be to list the functions that we're going to implement without any code yet. So one function I'm going to implement is the dunder repr function. This is just a representation. This is going to be traversing the list and printing the values, displaying the values that are part of the list. So here we're going to just say pass for now. We're also going to implement the contains dunder, which is of course going to check if a value exists in the list. This is what I showed you in my paint here a minute ago. And then we also are going to implement the length dunder, or the len dunder, which is going to give us the size of the list. And then we're going to implement a couple of methods that are not dunders. So one is going to be the append method. Obviously this is going to add a value to the list. It's going to add it at the end of the list. So for that, we're going to do pass as well. We're going to also have prepend, which is the opposite. We're going to insert it in the beginning. And this is what I meant when you have a doubly linked list. Actually, I messed it up. It's not the prepend. The prepend is easy with the normal linked list as well, because you just have to create a new node and let it point to the head node and then make it the head node. But if you want to append in the end, then a doubly linked list is useful, because you also have a tail, so you can do that in constant time as well. But we're going to take a look at that here in a second. So prepend is the opposite. You insert it as the first element, and then we have also the method insert. The insert method is adding a value to a specific index, to a specific position. And then we're also going to have delete, pop, get. So delete is going to be delete by value. So we provide a value, and this value has to be deleted from the linked list. Then pop is going to do that with an index. And get is going to give us the value of a specific index, of a specific position. And then we're also going to have a simple print function, which is going to be quite similar to the representation function, if not the same. And then finally, we're going to have a section down here, if name equals main. And here we're going to then create our class and use it. So these are the methods that we're going to implement. Now, if you want to take it easy, you can also drop some of them. You don't need prepend, you don't need insert necessarily. Whatever you want to do, it's going to be quite a lot of code here now. But you can also choose to just implement a couple of them. I would like to start with the append function, because that's the most, the first thing that you want to do with a list. You have an empty list, you want to add some elements to them, to the list. So how can we append a new element to a linked list? Now, obviously, if the head is none, I just have to set the head to the new node. So I can already have a case if self.head is none, so if I don't have anything in the list, all I have to do is I have to create a new node and make it the head of the list. So I can say self.head is equal to node value. That's quite easy. Now, what happens if I already do have a head? Well, then I just have to go to the next element as long as there is a next element, and at the end, when I see that now there is no longer a next element, I just have to create a new node and put it there. So this means I can say something like last equals self.head. So I start with a head, and I say while my last element that I looked at has a next element. So in the beginning it's the head. Does the head have a next element? If yes, go to it. Otherwise, append it already. So if there is a next element, I set last equal to this next element. So I go further and further into the list until there is no next element. And what I do then is I say last.next, since last.next at this point will be none, is going to be equal to a node given a value. So maybe I will do this here now with a graphical explanation. Just to give you the basic intuition, we have an empty list. So what do? I create a new node and give it a value. That's my append if the list is empty. Now, here my next pointer points to nothing. So what I do if I want to append 20, for example, is I go to this. I say while this has a next. Oh, it doesn't have one. So what I do is I create a new node here. Now, let's say I want to append 5 as a value. What I do is I go into the list. I see, okay, it does have a next element. So I set last equal to the next one. Okay, 20. Does this have a next element? No. Okay, perfect. Then create a new node and give it 5. Now, this here definitely has a runtime complexity of O of n. So we have to go through all the elements here necessarily to be able to append it. We don't have a reference to the last element. We don't have a tail element. So because of that, we cannot just append it in constant time. We have to go through all the elements to get to the end until we can then append a new element. So this is going to definitely have a runtime, or actually I'm not going to say runtime complexity, just O of n linear time. And this has a worst case complexity, which is linear, but it also has an average and best case complexity, which is linear, because you will have to go through all the elements. It doesn't matter. It's not a matter of chance or how well the data is structured or aligned. It's just you will have to go through all the data. So this is a linear runtime complexity here. Now, the prepend function is quite simple when we're talking about a linked list, because all we have to do is we have to create a new node. We have to make this new node point to the head, and then we have to make the head, or we have to make this node the new head. So all I have to do is I have to say first node is going to be equal to a node that has the value that I want to prepend. And then what I want to do is I want to say this first node then should point to the current head, and then the current head should be set to be equal to this first node. That's it. This also works if we have none. Think about it here again visually. Let's go to my paint. If I have a list like this, what do I have to do to prepend an element? Well, I just create a new node. Let's say I want to give it the value 25, for example. And all I have to do is I have to make it point to the current head, and then I have to say, okay, this is now my head. And if I have none, what do? I create a new element and I point to the current head, which is none. Still works. So that's quite simple, and this can be done in constant time. The list can be huge and it's still going to happen in the same amount of time because it's the same operation. So this has O of 1 O of 1 constant time. So linear time, constant time. And this is worst case, this is best case, this is average case, because every single time when I prepend a node, I will have to do this one operation. Create a node, let it point to the head, make it the head. That's it. Every time the same. Yeah, the insert is now a little bit more interesting because now we're going for a specific index. Now I want to say I want to put it at a specific position. Now we have one special case here. If this position, if the index that I'm trying to insert it into is 0, then I can just prepend. So I can say if the index that I'm passing here is 0, I can just say self.prepend value. because then I'm just doing the same thing that I just explained. Otherwise, we're going to do the following. We're going to say, first of all, if I don't have a head and I'm not trying, so if the list is empty and I'm trying to insert at an index that is not 0, then this should produce a value error because I'm obviously trying to access a position that doesn't exist. So we're going to also raise an exception here. We're going to say if self.head is none, and since we're not trying to use index 0, I'm going to raise a value error, and this value error will say index out of bounds. I'm not sure if the value error here is the correct exception type or error type, but let's just do it like this. So self head is none, raise value error, and otherwise if the head is not none, what we do is we say again last equals self.head, and we basically iterate using a for loop for I in range, and now we use the index -1 because we don't want to go to the element, we want to go before that element. And we're going to say if last.next is none at some point here before I get to the index that I'm trying to get to, I do the same thing as above. I just copy this and I paste it down here because this is also a problem. I'm trying to go, so if I want to insert at index 5, I have to go to one position before that because I don't want to go after the point where I want to insert. So I have to go -1. But if I, at this point, at somewhere during this process, if I realize that there is no next element, this means that I don't have enough positions to get to the index that I'm trying to get to. So again, index out of bounds. And if that doesn't happen, then I just say last equals last.next. And if the whole loop runs without raising an error, then I have the correct position. So what I do is I create a new node. I say this node has the value that I'm trying to insert. And then I say the new node dot next is going to be what this node is currently pointing to as next. I'm going to show you why that is visually here in a second again. And then I let this node here, the last node, point to the new node. So the idea here is if I have, let me just take my drawing tablet here. If I'm trying to insert something at this position here, what do I have to do that? Well, I create the node. Let's say the value is 30 here. I create this new node. What I need to do now is I need to ask, okay, what is the node before me pointing to, before myself pointing to? So the node that comes before where I want to insert this is 10. 10 is pointing to 20, so I just copy that. Now I point to 20. And now I say, okay, 10 no longer points to 20, 10 now points to me. This is exactly what we're doing in the code here. This is this here. We create a new node. We point this new node to the node that the last node was pointing to, and we'll let the last node point to ourselves, to the new node. That is it. And this, of course, has linear runtime complexity. In the worst case, I have to go. In the worst case, I have to go through all the elements because I'm providing an index that's, n or n-1. So that's linear runtime complexity. All right, so now we have the various methods to add elements to the linked list. Now let us talk about we're going to do the representation in the end, but let us talk about contains. How can I find out if something is part of the list? So this is a true-false function or method. This is going to give us either yes or no. And obviously, we do the same thing that we do when we do the appending, just that we can stop before that. We look for a value and we can terminate. So I think the average case runtime complexity is n divided by 2, so n half, because on average you will have to go through half of the list to find a value. But in the worst case, you will have to go through all of the list and you're still not going to find a value. So this has, obviously, before we even implement this, this has linear runtime complexity. Oh my God, what's happening here? There you go. Okay, so what we do here is obviously same concept. Last is equal to self.head, and then we say while last is not none. So while the thing that I'm looking at actually has is a node, is not empty, I check if the value of this is equal to, oh, actually we need to pass we need to pass a value here. So if last value equals that value, we're going to say return true. And then we're going to otherwise say that we want to go to the next element. So last equals last.next. And in the end, if I never return true, I have to return false. It's as simple as that. So we just do the exact same thing that I talked about. We start here. I'm looking for, let's say, 40, which is not part of the list. So I look at this element, no, next. Look at this, no, next. Look at this, no, next. Look, no, okay, end of the list. At some point, I don't have any values anymore. I get to this none, and then I have to terminate the loop, and I return false. And if I find the correct value in between, I just return true, and the function or the method terminates. All right. Now for the length, it depends on how you implement the linked list. This is something that you can implement differently. Now, if you just implement it the way that we have implemented it right now, calculating the length of the list has linear time, and it has actually also in the best case linear time, because what you have to do in order to count how many elements you have is you have to go through all the elements and increase a counter. So for example, with the current implementation, what we could do is we could say last equals self.head, counter equals 0, while last is not none. We say counter plus equals 1, last equals last.next, and in the end we return the counter. That is obviously in linear runtime because, of course, we have to go through all the elements until we get to the last one every single time. So it's not even average or best case in any other, it doesn't even have a different complexity when we look at the best case or the average case. We always have to go through all the elements, similar to append. However, you can make this constant if you change something about the class, if you, for example, also keep track of a size. So if you say self.size is 0, and every time you perform an operation, you update the size, which is not going to change your runtime complexity, you can make this constant. So for example, every time when I append, I can say self.size equals 1. And I can say here, when I append this, self.size plus equals 1. And so on and so forth. And I do that every time. I do that everywhere. So here I also increase, here I increase, and with all the delete methods we're going to implement, I decrease. In this way, all I would have to do is I would have to say return self.size, and that would make it a constant runtime complexity. You can do it like that. I'm going to now keep it like this. It depends on what you want to do, but this is not a bad thing. You know, if you're going to access the length frequently, it makes sense to have a single integer that represents the size. It doesn't really change the runtime complexity of any function, of any method. So that is definitely something that you could be doing, but I want to keep the code simple now, so I'm not going to mess with the size, just to focus on the operation itself. But again, you can make this constant by just updating the number every time the size changes. All right, so let's move on to the delete method. Now the delete method, what it does is obviously it tries to find the element. If it finds it, it updates the pointers accordingly. In other languages like C, you would have to free the memory. In Python, you just ignore it. You just let the nodes point to a different node now. But what we do here is basically we say again, last equals self.head. We start at the beginning and we say if last is not none already. Now, if it's none, I'm not going to do anything. So I don't even have to have an else branch here. I just say, okay, if it is none, do nothing. I mean, you could raise an exception, of course, if you want to, or an error. But I'm just going to ignore it. So if you try to delete a value that's not part of the list, I don't care. We're not going to do anything. What we're going to do is we're going to say if last value is equal to the value, we're going to say self.head is equal to last.next. So this is basically if we're finding the value already in the head. Otherwise, if it's not part of the head, we're going to run a while loop, while last.next. I'm not sure right now if this is even an efficient implementation. I don't even know if we need this if else statement, but yeah, let's keep it like this now. I prepared the code already. So while we have a next element, what we're going to do is we're going to say if the value of this next element, so we're already looking at the next element of its value, if that is equal to value, we have to look ahead because we need to perform the operation now, because if the next element has the value that we're trying to remove, we have to skip it. So we need to say last.next. I change this now to the next element. I'm going to show you that visually here again in a second. And then we break out of the loop. What's the logic behind this? Let me just again make this a little bit better here. So let's remove this here. Let's say we have, I don't know, it doesn't really matter what kind of values we have here, pointing to none. If I want to delete the 5, for example, what do I do here is I look at the next element. So here at 25, I look at 10. Is 10 5? No, obviously not. So what I do is I go next. At 10, I look at the next element. I see it's 5. Okay, I want to remove 5. How do I do that? All I have to do now, in Python at least, if I don't have to free memory, is I have to take the pointer that points to 5 and make it point to what 5 is pointing to. So I just have to skip the connection here. I just have to say 10 is now pointing to what 5 is pointing to, and it cuts the connection here. This connection theoretically still exists, so again, in other programming languages, you would have to free this memory, but now the list is 25, 10, 30, 40. So you just cut the connection here, and you redirect it to be pointing to what 5 is pointing to already. That's the idea here. Yeah, this is what we implemented. And of course, this is going to be in linear time. Why? Because in the worst case, you have to go through all the elements to find it. Now, this is not the average case, this is not the best case, but the worst case is linear time. Because chances are you're not going to find a value, chances are you're going to find a value at the very last position, which means you have to traverse n elements. For pop, it's different. For pop, we have to do it with the index. So again, we have to raise a couple of errors. First of all, if self head is none, we're going to raise an error right away. We're going to say index out of bounds. Otherwise, if the head is not none, we need to go through our iteration again. We need to say self, or we need to say last equals self.head. And we're going to say then that for I in range, again, index -1, we want to go one element before that, remember, so that we can skip the connection. We don't want to be at the element we want to remove, we want to be one before that, so we can redirect the next pointer. Here we're going to say if last next is none, which means that if I encounter none before I should encounter none, it means I don't have enough elements in the linked list, which means I will raise a value error, index out of bounds. And otherwise, I'm going to just go to the next element. And what I do then is I say if last next is none, which means that if the next element is exactly the one that I'm trying to remove, so basically the edge case that it's the last element that is none, that shouldn't be none, I still raise a value error. And otherwise, if that's not the case, what I do is I say last.next is equal to last.next next, which is again the exact same thing that we did here. Only difference is I go index-wise. So nothing changes here. I have the same logic, but I just go, okay, jump one forward. So if I have a certain index, I just go next, 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 index times, or index -1 times. And then I'm at the element that is one before the one that I want to delete. If that one that I want to delete is not none, then I just cut the connection to the next one. That's the same idea. And of course, depending on the index that I provide, this has linear runtime. You can see with linked lists, we have a lot of linear runtime complexity. Yeah, for get, obviously quite simple. If you want to get a certain value at a certain index, what you do is you say if self head is none, guess what? We raise a value error, same principle. The concept here is the same. The only difference is we don't do anything. We just return the value. So actually we have the same kind of iteration. We say last equals self.head. We say for I in range. Now we can use index because we don't need to stop one element before that, since we are not trying to perform any operation. We're not trying to change any connection. So we can just say go to the element, to the exact element, and then say if last next is none at some point here, then we're going to say raise value error index out of bounds, and otherwise go to the next element. So last equals last dot next. And if we can do that without any errors, the value I'm looking for is going to be the value of the last node I end up at. All right. And of course, guess what? Depending on the index that I provide, this is going to have linear runtime complexity. Perfect. So now we only have the print and the representation. And actually, it's not really complicated. It's just a styling thing, but it's the same kind of thing. We just iterate over the whole list and we print the elements. So we're going to say here, if self-head is none, return an empty list, or actually a string of an empty list. Otherwise, I do have some issue with my keyboard here. When I press E, sometimes it sends the key twice, and sometimes it doesn't send the key. I don't know why that is. I mean, it's a cheap keyboard, but maybe if you know the solution, let me know in the comment section down below. What we do here now is we say last equals self-head if it's not none, and then we iterate again. We say we craft a return string. This return string will start with a square bracket, and the first value in here, let's make this an F string. The first value in here will obviously be the self dot or last dot value. No, not return, sorry. Return is not so good. Return string. Now we're going to just iterate again. We're going to say while last has a next element. What we're going to do is we're going to say last equals last dot next. And then we're going to just say return string plus equals F string. And we're going to say comma last dot value. And in the end, we're going to close this off. We're going to say, now it's sent it 3 times. Did you see that? Return string. I need to get a new keyboard, I think. Is just a closing square bracket. And in the end, we'll return the return string. That's it. And obviously, this is always in linear time. Even in the best case, because you have to go through all the elements to display all the elements. Linear time, even in the best case. Now, actually, for the print, we're not going to use print. Actually, we're not going to do it. We're going to just say representation is enough. So these are the different methods. Now, let's see if I made some mistakes while implementing them. So let's go ahead and create a new linked list. LL is equal to linked list. And now let's append some values. Let's append the value 10. Now, let's say we want to have 5, and we want to have 18, and we want to have 22, and we want to have 29. And then maybe we want to prepend. We want to say prepend 100, for example. And then I want to print LL, for example. Let's see what this looks like. We have 100, 10, 5, 18, 22, 29. Looks perfect. Now let's say I want to insert an element. So let's say I want to say LL insert, and I want to insert the value 200 at position 1. So after 100. Now this also works perfect. Now let's say I want to delete the value 18 from the list. Now I get a problem. Okay, there is an issue with the delete function. What is that? Or with the delete method. Okay, I think it's quite a stupid mistake. I think here, when we're checking if the value is the correct value to remove, we say that it should be removed. Otherwise, however, we're not progressing. So we're not saying last next equals, or actually last equals last next. I think this is what it boils down to. There you go. So now 18 is deleted. Wasn't that big of a mistake. Now let's go ahead and say ll pop. Now let's pop index 1, which means the 200 should be gone now. There you go. And did we have anything else? We had prepend, insert, delete, pop. I mean, we can do get. So if I say print ll get index 1, and if I say, for example, print 29 in ll and print, I don't know, 800 in ll, there you go. I get index 1 is 10, I get 29 is in ll, yes, 800 is in ll, no. So that is how we can implement a simple single linked list. Now, how would we change this to a doubly linked list? Well, we would have to change, first of all, how the node works. So we would have to say every node now doesn't have just a next pointer. Every node now also has a previous pointer. So self.previous is none by default. And then we also have for each linked list a tail. So self-tail equals none. Now this gets tricky now, especially because you have to sometimes, or the first time you add something, you have to make it the head and the tail, but then you have to always keep adjusting both values. So now let's call this doubly linked list. Now for the representation function, it doesn't really matter, because to represent this, we have to go from beginning to end. The tail is not important, so we can keep this function exactly the same. Same for the contains function. If we just iterate over the list to get a certain position, it doesn't really matter. I think the same is true for the get function. The get function doesn't change at all, and the length function doesn't change. So this doesn't change, this doesn't change, this doesn't change, and this doesn't change, because we don't change anything about the list. We don't have to adjust anything. But we will have to change the way the append function works, or method works, and all the other methods that actually manipulate the content of the linked list. Now, what we need to do here is, if we append a value to an empty list, we have to set the head equal to the node, but we also have to say that the tail is equal to the head. So we have to basically say now, since we just have a single element, the head and the tail of the list is the same. This is obviously the case. However, if we append something to an existing list, this is easier now because we just have to append it to the end. So we can actually, instead of iterating here, we can say now the last node, we do basically the same thing that we do here with the prepend. We say the last node is now a new node with a value. The last node says that it points, or has to point now, to the previous node, which is the actual tail right now. So self.tail, I'm going to show this here visually in a second again. Self.tail next is going to be equal to the last node, and self.tail is now the last node. So think about it that way. Let me get my fancy drawing tablet again. Let's say we have a doubly linked list. I have this structure here. Now, of course, in both directions. And of course, we have a null pointer here and a null pointer here. Now, we do have some values, it doesn't really matter. If I want to now append an element, so add an element to the end of the list, and let's say we have a in the list here, we have head and we have tail. If I want to append an element, all I have to do is I have to create this new element. I have to make it point to the tail as a previous element. The default for the next is null anyways, or none. And now I have to just say that this element here, instead of pointing to nothing, points to this new node. So maybe to illustrate this better, I have a new element down here. I let it point to the previous element, which is the current tail. I redirect the pointer of the previous element for the next element to this new element. This points to none, obviously. And I then say that the new tail of my linked list is now this. That's exactly what we did here. And this can be done in, now we changed the runtime complexity, this can be done in constant time, similar to the prepend. Constant time. Now the same is true for prepend, but we need to adjust it. So this is now basically the same idea, but we need to say again, if self.head is none, we need to set head and tail to the same thing. So self head is going to be node value, self tail is going to be self head, and otherwise we do the same thing as before. So we create first node is node, last node or first node, next is the head. The head is set to the first node, but before that we need to say self head next is going to be equal, or actually no, self head previous is going to be equal to the first node. Yeah, that's how we do it. And again, this remains in constant time. Now for the insert, we don't really change much. The whole structure is the same. The only thing is, I mean, all of this stays the same, the iteration, but in the end, we need to also adjust the previous pointer. So we say new node equals node value, new node next equals last next, but now we also need to say new node previous is equal to last. And then last next is new node. So this just means that when you insert a new node, you need to make sure that when you insert it here, it doesn't just point to the next element, it also points to the previous one, and then you adjust these pointers accordingly as well. Let me just think about this again. Do we do this here? We say new node next is equal to last next, new node previous is equal to last. No, actually we need to also set the previous. We're not doing this here. My prepared code is not that prepared, it seems. So let me think about this here on the fly while I'm doing this. I think we need to say, before we set last next equal to new node, we need to say last next previous is equal to new node. I'm not sure about this. We're going to see if we run into problems, but I think this is what we need to do. Because as I said, let's look at the graph here. When I insert an element, what I want to do is I want to cut these connections, or actually before I cut them, I want to create a new node. I want to say, okay, I want to point as the next element to this node that this is pointing to. I want to point to this as the previous element, but then I also want the next element here to be pointing at me and the previous element here to be pointing at me. And then I want to cut these connections. I think we're doing this now. If not, we're going to notice and fix this. I hope so. Delete. Now here we actually do it properly. Here we actually progress. So let me see, do we have to change much? Well, when I delete an element, I have to delete the next reference, but I also have to delete the previous references. So yeah, so I also don't have this prepared in my prepared code. Okay, so we have to do some things here on the fly. Seems like I didn't invest a lot of thought into my doubly linked list here. Okay, but if I'm not mistaken, the only thing that we should have to do here is we need to say last next previous is equal to last next. Yeah. And then last next is equal to last next next. Does this make sense? Not sure. We're going to find out. If not, we're going to fix this. This is also a nice experience here. For pop, we do probably the same thing. So we just say iterate, that's fine. And then here we say last next is equal to last next next. But before that, we do last next next previous is equal to last. Actually, I think this is what we need to do here as well. We need to say last next next previous is equal to last, not to last next, I think. And for the get, we don't change anything. So let's see now. This is a doubly linked list. We're gonna still call it LL. Let's see if all of this still works. First of all, yes, it produces the same results, which is good. Now, how could we get this to fail? By inserting and deleting. So by inserting all these values, Actually, for the insert, I should also have the case. Oh no, actually I don't have the length. So if I keep track of the size, I can say if index is size, just append. But that doesn't make a lot of sense here. So let's say instead of appending, we're going to insert. We're going to always insert. Actually, I'm going to append the first one, but then I'm going to insert at position 1, for example. Or actually, I'm going to always insert at position 1. 10, or actually, let's use different numbers. 20, 18, 22, 88, 97, that's a 0, not a 9. Then prepend, and then insert again, and then try to delete 18, and try to delete 22, and try to delete 5. And then pop 1. Let's see if this makes sense. Okay, you see, there's a problem. None type object has no attribute previous. Yeah, of course, because we need to also make sure this is now not irrelevant. If we have the if we have a none, we need to make sure that actually we don't try to set previous. So where did I do that? I did that with delete. So here we need to say if last next next is not none, then we want to do this. And here as well. If last next next is not none. This was actually not the problem. Last next previous. Oh, this is an insert. Okay. So new node previous, that is the thing. If last next is not none. Okay, let's double check this to see if this is what we would expect. We append 10, so the first element is 10. 5 comes after that, so 5 should be after 10. 20 should be after 10. 18 should be after 10. No, actually not. Let me try to see what I would do manually here to see if this actually works. So I would say 10, then I would say 5, and then I would insert everything before that. So it would be 20. So it would be actually 97, 88, 22, 18, 25. Then I prepend 100. And then what I do is I delete 18. I delete 22. I delete 5. And I pop 1. So I should have 100, 97, 88, 20. Okay, 10 is not removed. Why is 10 not removed? Or did I make a mistake here? Let me see again. Does pop not work? What happens if I don't do pop? Oh, I forgot to insert 200. So this actually should work. Yeah, okay, actually it works. Because now I would just pop. Again, I insert all these values, then I prepend 100, but I also insert 200, so I delete 18, 22, and 5. Then I pop 200, yeah, and then I end up with this. So I hope there are not any more mistakes in my implementation, but that is exactly what you would expect here. So yeah, this is how you implement a linked list and a doubly linked list in Python. I hope you were also able to understand why the runtime complexities are what they are. When we talk about runtime complexity, we always talk about worst case, unless we specifically say we talk about best case and average case. But yeah, so let me know if you like this in the comment section down below. Alright, so we're going to implement a stack data structure as the second data structure in this tutorial series today, and similar to last time, I would like to start by giving you a brief theoretical explanation of what a stack is and how it works. It's quite simple. This data structure doesn't have too many operations. The basic idea of a stack is we have blocks, let's say, that contain certain values, and what we do is we stack them on top of one another. So for example, here I have the block with the value 10, and what I can do now is I can add a new block on top of it with a value 20, for example, and then I can add a new block on top of that with a value 5, for example, and I can do that, and this operation of adding a new block on top is called the push operation. So I take a new block and I push it on top of the stack. Now, the second operation, the second major operation of a stack is taking the top element and processing it. So taking, for example, if this is the top element of 5 and doing something with it and removing it from the top of the stack. This operation is called the pop operation. So these are the two major operations. I add a new element on top, or I take the top element and process it and remove it from the stack. So push and pop. And then there's also the third operation here called peek, which is basically just looking at the top element without processing it. So just taking a look, what is it? And that's basically it. And of course, we can also implement things like print the whole stack, so iterate through it and print all the elements, or things like checking if the stack is empty. But these are the three major operations: pushing, popping, and peeking. Now, a stack is a data structure that operates according to the LIFO principle. So last in, first out, which is the opposite of a queue. We're going to talk about the queue soon in this tutorial series. But the basic idea is the element that was added last to the stack will be the first one to be processed. So it's not the same as a queue where the first person that enters a queue is the first person that leaves a queue. It's the last element that was put on top of the stack is going to be the first one that is popped out of the stack. And this has a bunch of use cases, which I'm not going to talk about here in this video today, but that is the basic idea of a stack. And this is what we're going to implement now in Python from scratch, core Python, without imports, just with classes. And as I said, core Python. So we're going to open up a new file here, which I'm going to call stack.py. And the stack now is still going to be based around a node class. So similar to the linked list, we're going to have a node class. Actually, we're going to have the exact same node class, which is going to have a value and a pointer to the next element. In this case, next is the element below the current element in the stack, if there is one. So we're going to say class node, and we're going to define the init method here to take a value as a parameter, and to say self value is equal to values, self next is equal to none by default. And the stack class now is also similar to a linked list, has a top element, which is similar to the head element, but this element is always just a top element, and we always just work with this element. So we always just either add something on top. So we could say in terms of a linked list, we always prepend, or we always just pop the most top element. We always pop the head, so to say. So here we can say def init, and we're going to say self dot top equals none, and we're also going to keep track of the size today. So we're going to start with the size of 0, because we don't really have to change much when it comes to a stack and updating the size. So we can easily implement already the length function, which is going to just return self.size, and I don't think it's a surprise when I tell you that this is possible in O of 1, so this takes constant time, constant runtime complexity, because we always just have to return a single value, which is updated in the other methods. So that is the length under. We also are going to implement the representation, but not yet. So I'm going to do that in the end. So just pass for now. We're going to also implement the push method, which is going to push a new value on top of the stack. We're going to implement the pop method, and we're going to implement the peek method. And then we're also going to implement the simple isEmpty method. Now actually we can do this already. We can just say return self top is none. That's it. So the important thing about the pop is it actually returns the item. So it's not just popping it out of the stack and then removing it. We also return the item. This is the difference between, for example, the pop, or actually maybe I should have implemented that also in the linked list like that, but the difference here is that we actually return the value. We want to process it. So let us start with the push. Let's say we want to add a new element on top of the stack. How do we do that? Well, it's basically just a prepend function of the linked list. So if we don't have a top element, so if self.top is none, what I do is, or actually I don't even have to do that. I can do that simpler. I can just say create a new node and let it point to the previous top, because even if it's none, I just point to none, which is fine. So I can just say here that my new node is going to be equal to a node that has the value, and then the new node next should be just pointing at self.top, and then I want to set self.top equal to the new node. So, and of course we want to say self.size plus equals 1. So if we look at our graph here, the basic idea is that if I have, let's go back a little bit here. If I have this stack here, and let's say we don't have any dots up here. If I want to add a new element, what I have to do is I just have to create this new block with a certain value. Now I'm using my mouse. This is why this doesn't look so good. If I say, oh, this looks horrible. If I say this is 6 now, all I have to do is I have to say 6 now points with the next pointer to the 5 element, and I have to set the top reference in my stack to this element. That's all I have to do. This is quite simple, and of course this works in constant time. So this works again in O of 1 constant time. And you will notice that the stack operations always take constant time, except for maybe the representation here, but they have a very limited use case, or very limited use cases, but they all work in constant time. So for the pop method, what we have to do is we have to say if self.top is none, then of course it doesn't work. I cannot pop an element from an empty stack. It doesn't work. So I have to say raise value error and then stack is empty. And otherwise, what do I have to do? I basically have to get the value. So I have to say the value I'm popping here is the value of the topmost element, because I want to return it, right? And then I have to say self.top is whatever the next element is. So self.top is self.top next. Self.size has to be decreased by 1. And in the end, I return the pop value. Again, visually speaking, what does that mean? It means that 5 is my topmost element here. So what I do is I get the value 5 because I need to return it. And then I just say, okay, my top pointer of the stack is now not pointing to 5, but to whatever 5 was pointing to as the next element. So my top pointer is now located or pointing to 20, and I have the value 5, which I return to the person calling the function. And of course, this is possible in constant time, because all I have to do is I have to take the top element. I don't have to go through the stack. It doesn't matter how large the stack is. I just look at the top element and I point to the next one and I return the value. It's always the same, even if I have a million elements. So constant time. And peak is even simpler. Peak is just basically saying if self-top is none, then I can raise a value error. Stack is empty. And otherwise, I can just return self-top value without doing anything. So I'm just looking at the value, but I'm not popping it out of the stack. And of course, again, this works in constant time. And of course, this as well. This also works in constant time. The only thing that does not work in constant time is if I want to print the whole content of the stack, which usually I don't want to do, but if I want to do that, it takes linear time because I have to go through all the elements. So even in the best case, it takes a linear, even in the best case, it has linear runtime complexity because I have to go through all the elements. So items is equal to an empty list, and then I'm just going to say current item is self.top, and then I say while current item is not none. So while the current item is actually an item, I say items append string version of the current item. We can do that because we have, or actually, can we do that? Current item value, we should say. So because our node doesn't have a representation function, we have to access the value. So we append to the items list the value, and then we're going to say current item is equal to current item next. This goes as long as I have some value that is not none. or some note that is not none, and then I join all of this together here on commas. This is one way to do that. Last time we did it with crafting a string. This is another way to do that. We gotta have variety here. And this, of course, as I said, needs linear runtime complexity. All right, so let's see if this works. For this, we're going to open up a section down here, if name equals main. And what we're going to do now here is we're going to create a stack. We're going to say stack is equal to stack. And then we're going to just say stack dot push. Let's push a couple of values into the stack here. Then maybe something like this. There you go. And then print stack. And then maybe stack dot peak to see the top value. And then maybe stack dot pop, which is also something that we can print. And maybe in between, you want to also print the full stack to see what's happening. Maybe I can just take this and copy this a couple of times. And of course, I can also, in the end, try to see if stack is empty, but that's what we do. We say 12, 6, 16, 14, 10. So this is the stack. Since I pushed 12 last, 12 is the topmost element. So if I print the stack, I get this first. If I peek, I get this first. If I pop, I get this first, and so on and so forth. And in the end, I only have 10. So if I pop one more time, I should probably get an empty stack. Or do I get an empty stack? If I pop one more time, it should then probably crash. There you go, stack is empty, works. And I should also be able to say print stack is empty. This should give me a true now, but it should not give me a true if I do it up here. And I get true here, false here, perfect, works. So that is how you can implement a simple stack data structure in Python. Next time we're going to talk about the queue, which is quite similar, just that it has the opposite order. So first in, first out. This time we have last in, first out, which means last element to enter is the first to leave, and the queue works the opposite way. All right, so we're going to implement the queue data structure from scratch in Python today. And as always, I want to start by giving you a brief theoretical explanation of the data structure so you know what it is that we're implementing here. And for this, I want to use my paint again. So in the last video, we talked about the stack data structure. And the stack was just a bunch of blocks of data stacked on top of one another. And we had a top of the stack. So we had a top element of the stack. And the three major operations were I can push new stuff onto the stack. So I can take a block of data and put it on top of the stack. I can pop stuff out of the stack. So I can take the top element, remove it from the stack, or I can just look at the top. So I can just see what's there by peeking at the stack. And this principle of pushing something on top of it and taking that element as the first element to be popped when we use the pop operation, this is the LIFO principle. So this is last in, first out. The last element I push on top of the stack is the first one to leave the stack when I use the pop operation. Now the queue is exactly the opposite of that. The queue says first in, first out. So a queue operates according to the first in, or FIFO principle, first in, first out principle. So it's literally a queue, like a queue of people. You have a front, and what you can do is you can enqueue elements. So the operation here is called enqueue, like this. And let's say at the front we have a block of data, and then we have another block of data and another one. If I now want to enqueue an element, what I do is I just put it at the rear end of the queue. So whatever I put into the queue, whatever I enqueue, is added to the rear, to the end of the queue. And when I use the dequeue operation, I take the element from the front. So whatever enters the queue last is also whatever enters the whatever leaves the queue last, and whatever enters the queue first is whatever leaves the queue first. So it's literally like a queue when you are in a restaurant or something. So this is the first in, first out principle, and we still have stuff like peeking, so we can still look at the next element to be dequeued, we can still do a peek, but that's the difference here. We don't have the LIFO, we have the FIFO principle. Whatever enters the queue first is also the first thing that leaves the queue. And that is a different data structure. This is a different way of working with data, and it also requires slightly different implementations here. So let us get started with the code. We're going to create a new file here, queue.py, and we're going to still base this around a node. So we're still going to say here that we have a class node, and this node has a constructor which takes a value. So this is going to be the value of the node. And the node is also going to point to the next node. So it's also going to have the next reference here, which is going to be set to none by default. So that stays the same. This is not too special here. Now, the difference between a queue and a stack is that we also now keep track of the rare end of the queue, because we need to append new elements to the rare end of the queue, and we need to pop them out, or we need to dequeue them from the front. So we need to have a front reference and a rare reference for this to make sense. So we're saying here now class queue, and this class queue has a constructor, and this constructor says the following: self.front is equal to none, self.rare is equal to none, and self.size is equal to 0. Just so we can make the length calculation quite easy. So we can just say, if I have the dunder length, I can just say return self size. Now, of course, I need to keep track of the size. I need to increase it and decrease it accordingly, but this is not too difficult here. Every time I enqueue something, I just add 1, and every time I dequeue something, I remove 1. Besides that, let's also go for a representation dunder. So for the string representation of that, I'm just going to pass for now. So I'm just going to define the methods that we're going to need. We are going to obviously need an enqueue method. So enqueue self and value. We are going to use dequeue as well. And this kind of data structure is obviously very useful. For example, I have some tutorials where I did that. You have connections or elements to process. Maybe you use 10 threads or 10 processes to do something, and you don't want to process the same elements twice. So you have a queue, and the next element to be processed is not from a list where you have to work with the indices. You just take the element out of the queue, and then the next process cannot take the same element because it's no longer in the queue. That would be a use case for the queue data structure. As I said, we're going to use the peek method as well, or the peek method. Actually, we don't need a value here for dequeue. Sorry about that. And we're going to use something like isEmpty, which is optional, but let's just implement it. All right, so how do we do these things? We're going to do this one later on. Let's focus on enqueuing and dequeuing. Now, enqueuing is quite simple. What we do is we create a new node. And the new node is going to have the value. And what we do with this new node now depends on whether we have something in the queue already or not. So if self.rare is none, this also means that self.front is none, because if I only have one element, it's going to be the same. So if there is nothing in the queue, what I'm going to do is I'm just going to say self.front is equal to self.rare is equal to new node. So I say the front and the rare are the same object, new node. If, however, I already have elements in the queue, so else, what I do is I say self.rare.next is going to be equal to new node, and then self.rare itself is going to be set to new node. So basically, maybe if we look at this graphically, I'm going to use my mouse now, so this is not going to be very beautiful. If I have here F for front, and if I have R for rare, if I have nothing, these are pointing to none. If I have one element, like this block here, both are pointing to this element. So my front and my rare element are the same. And if I now add a new node, what I have to do is I have to say that this is still pointing to this here, right? So I have to say that this thing has to point now to the next element, but also I want to reset the pointer of rare. This is difficult with the mouse. I also want to reset the pointer of rare to be pointing to this new node. So this is exactly what we're doing here in the enqueue method. And of course, don't forget to set the size or to increase the size by 1. That's it. That's the magic of enqueuing data. Dequeuing now is obviously also not too difficult. What we do is we take the element from the front. Now, if there is no front element, we raise an exception. So we don't want to have any call to dequeue if the queue is empty. So we're going to say if self.front is none. If that's the case, we raise, let's say, an index error. Now, I'm always not sure which one of these errors is the correct one, but I think index error makes sense here. So let's say queue is empty. Otherwise, what I want to do is I want to say the dequeue value is equal to self.front.value. So I get the value of the first node of the queue, and then I say that my front element should now be pointing to the next element. So I say self front is equal to self front next. This could be none, of course. And now if self.front is none as a result of that, so if I'm actually pointing to none now, then rare should also be none. Yeah, this makes sense. And of course, every time we want to say self.size minus equals 1. So again, what's the idea here? If I have this structure here, now let me actually use my drawing tablet here, because otherwise this doesn't look very good. So if I have this structure here, I'm pointing to this as my rare node, this is my front node. If I just take this out of the queue now, I say that my front element is now pointing to this directly. And if I remove this as well by dequeuing it, then my front element, of course, points to nothing now. So to none. But this one still points to something else, so I also need to make this point to none. That's the basic idea of what we're doing here. Dequeuing means size minus 1, enqueuing means size plus 1, okay? And peaking is quite simple. All we have to do in order to peak is we have to copy this, and basically instead of storing it, we can just immediately return it. So I can just say return self front value. That's it. We don't need to do anything. And isEmpty is actually quite simple. We just say return self front is none. That is the queue data structure. That's basically it. There's nothing too difficult about this. We just have, actually we need to implement the representation dunder, but that's basically it. You just go through, you don't even have to go through the elements because you just use the front or the rare to do stuff. We're going to talk about the runtime complexities here in a second. But let's briefly implement the representation dunder. We're going to say items is going to be equal to an empty list. We're going to say current item is going to be equal to self front. We're going to say while current item is not none. We're going to just append it to the items list, and then we're going to move to the next one. So we're going to say items append. And then we're going to append the string version of the current item dot value. And we're going to say current item equals current item next. And in the end, we're going to say return, comma, join items. I think this should work. And now let us talk about the runtime complexity. Now, obviously, the length function, the length dunder, has constant runtime complexity because all I have to do is I have to look at the value. I just have to call a single variable. If I have 5 million elements in the queue, this doesn't change. I just have a different number. I just have a size of 5 million, but that's it. I just have to say, okay, look up the value, return the value. So that is obviously in constant time, which is the best thing that you can have. Now, the representation dunder is in linear time. Why? Because I have to go through all the elements. I have to go through every single node in the queue to get all the elements. So to print all of them, I have to iterate through all of them. So in the best case, worst case, average case, this is an O of n, linear time. In queuing an element, these are now interesting because these are the main operations. In queuing an element is also done in constant time. Why? Because all I have to do is I have to look at the rare and I have to append an element. Now, maybe I have to also adjust the front, but that's not really that much of an issue. So this is done in constant time. There is nothing difficult about this. I just have to look at the rare and I have to append if there is already a rare. Otherwise, I just have to create the first element of the queue. That can be done with the same amount of effort regardless of how many elements I have. If I have 5 million elements, all I have to do is I have to go to the last one, which I have a pointer to, a reference to. All I have to do is I have to append a new node there. I just have to create the next reference to a new node. Always the same effort. And of course, you guessed it, this is also the case for dequeuing, because all I have to do, even if I have 5 million elements, it doesn't matter. I just take the first element from the front of the queue and I remove it and I adjust the front pointer. That's the same action I take every single time, regardless of if I have 5 million, or 5 billion elements in the queue. So that is O1 constant time. Peaking, trivially as well, all I do here is I just look at the first element. I just have to call, or not call, I have to go to the reference and look at the value. That's it. And this empty is also done in constant time. So you can see that these operations are quite efficient. All of them are done in constant time. The only thing that takes linear time is iterating over all the elements. But of course, if you want to iterate over all the elements, you have to iterate over all the elements, which is n. So this is going to be linear. So that's it. Let us go and try some stuff. So let's say if name equals main. And now we're going to create a queue. The queue is going to be a queue. And we can play around now with enqueuing, dequeuing. So let's just say queue and queue 10. And then I can just say 20, 30, 40, 50, 60. And then I can print the queue. I can print the length of the queue to see that the dunder works. And I can print, or actually I can say queue dequeue, and I can print these elements. And then I can print the queue again. And also the length. And what I get here is I get 10, 20, 30, 40, 50, 60. Then the length of the queue is 6, correct? Queue dequeue, none. Why is that? Let me see what the problem is here. Maybe I'm not returning. I think I'm not returning, right? Yes, of course. We need to return the dequeue value. Otherwise, this doesn't work. There you go. I mean, it still pops it out of the queue, but it doesn't show it. So 10, 20, 30, which are the first elements I added to the queue, are the first elements to leave the queue. Now I have 40, 50, 60 left, and 3 is also the correct length. So there you go. This is the implementation of a queue from scratch in Python. Alright, so we're going to implement the hash map data structure from scratch in Python today, and as always I want to start by giving you a theoretical explanation of what a hash map is and how it basically works before we jump right into the coding, and as always we're going to do that here in MyPaint. Now, the basic idea of a hash map, or also oftentimes called hash table or dictionary, is that we have so-called key value pairs. So we always have some key, like key 1 for example, pointing to some value 1. And every key can only have a single value. Now values can occur multiple times, but keys are unique. So key 2 can point also to a value 1, but we cannot have key 2 then pointing to something else. So I could have key 3 pointing to value 2 or whatever. That's the basic idea. We have a key, and this key leads us to the value. This is the principle. This is how it works in general. The interesting thing about a data structure is, of course, how does this work? And this works with a hash function. This is why it's called a hash map. And it works by passing a key into a hash map, into a hash function, and as a result getting an index where to find something. So we're going to implement our own hash function in this video today, but let's for now just consider the hash function to be a magic black box. All we do with this hash function is we feed in a key, some key 1 for example, and as a result we get a position in a list, in an array. So we get some index. And this is deterministic. For the same key, I'm always going to get the same index. And the idea now is that the key is basically what I input into the hash function to get a calculated result. So I don't have to iterate, I don't have to search, I don't have to go through all the possible branches of a tree or something. I just calculate an index based on the key with a hash function. And this index then leads me to a position where I can find a value. So if we consider that we have some basic list here with elements 5 and 10 and 30, and maybe we also have some strings here like Mike, and maybe we have, I don't know, some booleans here like true or whatever. Doesn't really matter. We have some elements in the list here. And instead of providing now the index, what I can do, of course, is I can say I have index 0, 1, 2, 3, 4. Instead of saying I want to find the value Mike, or I want to find the value at index 3, which is of course also simple. If you know the index, you can just jump to the index. But if you don't know the index, you have to search. And what we do now with a hash map or with a key value pair is I have this hash function. When I input the key name, for example, into this hash function, as a result, I get 3. That's the basic idea. Now, why do I get exactly 3? It doesn't really matter. Let's say I don't have Mike in the list yet, and I want to store the name. So I want to store the value Mike with the key name. So what I do is I feed the name into the hash function. As a result, I get 3. And what I do then is I place Mike at this position. That's the basic idea. Why do I do that? Because the next time I want to find Mike, I want to find the value for the key name, I just have to do the same thing. Hash the name, get 3 as a result, and instead of looking through all the positions here to find Mike, I just know, okay, position 3. Jump there immediately. So in the best case, or in a good case, in a convenient case, this can be done in constant time. Constant time. Why? Because that's just a calculation here. We're going to talk about this here, but this is just a calculation. I get the key and jump to the corresponding index. I don't have to iterate over the elements. It doesn't matter how many elements I have here. If I have a unique position for every input here, I can just jump there. Practically speaking, there are some difficulties, and these difficulties are that hash functions produce different values, produce the same values for different inputs. So maybe I have the key, I don't know, job or something, and for some reason, again, let's consider this a magic black box. For some reason, when I feed job into the hash, I also get 3. So this is called a collision. This means that, for example, if I want to store the job programmer, what's going to happen now is that it's going to recognize, okay, index 3, but it's going to see, oh, I already have a value here. And the question is now, how do I resolve a collision? This is called collision handling. So collision handling, and it can be approached in different ways. One way, for example, is if I have a fixed size, let's say I have, for example, here some empty space, and then again some value, would be to just jump to the next free position. So it would be something like, okay, I already have Mike in here. I want to store programmer for job. So what I do is I jump to 3. Okay, 3 is already taken. Let's go to the next one. Oh, 4 is also taken. Let's go to the next one. Oh, this is free. So let me store programmer here. That's the basic idea. I jump until I find a free spot. And of course, what happens now is that if I want to find programmer, if I want to find job, what I do is I say hash, I see 3, I see this is not what I'm looking for, this is also not what I'm looking for, this is what I'm looking for. So I'm jumping again. So practically speaking, if I have a good hash function that gives me good indices for the different inputs, I can expect to have constant runtime on average. However, in the very worst case, what's going to happen is that I have a list with a couple of free slots, and let's say my hash function is very stupid. Every time I put something into it, every single time it produces 1 for some reason. For job, for name, for age, for anything that I put in here, I get 1 as a result. What's going to happen then is everything is going to be placed at 1. So I'm going to have stuff like Mike, I'm going to have stuff like programmer, I'm going to have stuff like 30 and true and all this stuff. And every single time I want to look up something, I'm going to land here and have to jump through all these elements to find my element. So in the worst case, I'm going to end up with linear runtime complexity. In the very worst case, I have to go through all the elements until I find my element. That's the worst case. But with a good hash function, we can get an average case of constant time. Average case complexity, which is constant. Now, we here are not going to use this collision handling. In our implementation, we're going to use buckets, which means we're going to have lists of, or we're going to have a list of lists. So instead of having slots, I'm going to have lists. And this means that if I now try to input for name, Mike, for name I try to hash and I get 3, what's going to happen is I'm going to add Mike in here. So I'm going to say that my list here now is going to be Mike. And when I get the new value job, or the new key value pair job programmer, and for some reason my hash function gives me a 3 again, I'm just going to append it to the list. So I'm going to say programmer. And that is going to be how I handle collision. So I'm not going to just shift it. So to keep the size dynamic, we're going to have these buckets. But that's the basic collision handling that we're going to do. We're going to have multiple values. And then, of course, if I land here, I have to iterate over them until I find the element that I'm looking for. That's what we're going to do here. This can still, of course, lead to the problem of worst case linear runtime complexity, because all of the elements can end up in the same bucket, and then you just have a list. Then you just have to treat it like a linked list and look at all the different elements in there. This was a little bit longer of a theoretical explanation now, but I think it's important to understand how this works and why this works, and now we're going to implement this. Now we're going to write the corresponding Python code for this. So I'm going to say here hash underscore map py, and we're going to create a class hash map. So this time we don't have a node. Finally, we have just a single class hash map. And what we're going to define here in the constructor is we're going to say a hash map starts with a capacity. Now, for Python purposes, this is not really that much of a difference, especially with our buckets implementation, because if you use something like C, you would have to, or any language that has fixed sized lists, you have to keep track of the size, and you need to make sure that you don't exceed the capacity. In Python, it's not really an issue. So in our case, this is just going to be how many buckets we have, but the buckets have limitless capacity. I mean, of course, you have a RAM limitation, but programmatically speaking, I can have buckets that are very long. So the capacity is just going to be the number of buckets in our case. But if you're implementing this in C, you want to take care of the capacity of the size, and you want to resize maybe if you want to keep this dynamic. But here now we're going to use the convenience of Python and just say the capacity is the number of buckets. And besides that, I can store an infinite amount of elements in my hash map. So self capacity, and then we're going to say self capacity equals capacity, self dot size is going to be equal to 0. The difference here between size and capacity being capacity is the number of buckets, size is the number of elements in the hash map, and then we're going to say self.buckets is going to be empty lists for placeholder in range capacity. There you go. Okay. So that's just the initialization. Let's start with the basic stuff again. We're going to define the methods that we're going to use. So we're going to have obviously a length method, or a dunder length. I'm going to pass for now again. I'm going to have a representation dunder. Or actually, we don't need, do we need a representation dunder? I don't think that I implemented one in my prepared code. So let's actually just print the buckets if we're interested in that. Let's not use the representation. But we're going to use the contains dunder. So to see if something is part of the hash map. For this, we're going to do it in the same way that Python dictionaries do that. We're going to see if we have a key present. So actually, we need to also say key here. Then we're going to have put. The operation put means we're putting in a new key value pair. So key and value are going to be part of that. Then we want to have get. Get means we provide the key and want to get the corresponding value. And then we want to say remove, which is going to remove the value or the key value pair for a certain key. And then we want to have these typical dictionary methods. We have keys, we have values, and we have items. This is the same that we have in a dictionary in Python. So keys will give us the list of all the keys, values of all the values, and items will give us the key value pairs. And then we have one important function, the most important function, the black box here, which is our hash function. I'm going to make this private with an underscore here. That's just going to be a helper function that's in the class. And this is going to take in a key and return the index, the position. Now, for this here, you can use whatever you want. It just has to fit certain properties. You need to produce, as a result of this function, you need to get an index that's part of the, that's within the capacity. So if you have a hash function that produces values like 5,000 or maybe even with characters in them, that's not what you want to have. You want to have a hash function that gives you an index that's smaller than the capacity. But besides that, it doesn't really matter what you do here. Of course, it matters in terms of performance and runtime complexity, but it doesn't really matter in terms of it works. But of course, an intelligent hash function will lead you closer to the ideal of having constant runtime complexity. And if you use a very bad hash function like always returning 0 or always returning 1, you're going to have the problem that you're ending up with worse average runtime complexity. So our hash function is going to be a simple polynomial rolling hash. We don't need to really get into this too much, but the basic idea is we're going to create a string version of our key. So I'm going to say key string is going to be equal to str key. And we're then going to iterate over the individual characters, get their ASCII codes because we need to work with numbers. So we are going to allow strings as keys as well, but we're going to have to use the ASCII codes to do calculations because we need to work with numbers here. So key string is going to be string of key, and then we're going to say the hash result is going to be 0 in the beginning, and we're going to say for every character in our key string, we're going to say that the hash result should be equal to taking the current hash result, so in the beginning 0, times 31 plus, and then the ASCII code of the character, and the most important thing, modulo self.capacity. Why is that so important? Because by saying modulo self-capacity, we will never get the capacity or larger. We will always have a number that is between 0 and capacity minus 1. So that is exactly what we need. So anything modulo self-capacity will be good or will be functional. It won't be necessarily good, but that is what you need as a hash function. So something that gives you a value between 0 and capacity minus 1 as a result of a key. And of course, deterministically. So generating a random int between 0 and this capacity minus 1 boundary doesn't do it. You need to always get the same result. Yeah. So that's our hash function here. And now we can get into the implementation. For the length dunder, it's quite simple. Just return self.size, which again means we need to keep track of that. For contains, it's also quite simple because since we're going to have, we're not going to use the keys function here. We're going to say for each bucket, we're going to see if the key is there, if we find the key. So we're going to say here, index is equal to self.hash function key. And we're going to basically go to the bucket. So bucket is equal to self buckets index. And then if we have multiple elements in there, we're going to just say for key value pair in this bucket, if key is equal to key, what I want to do is just return true. Otherwise, return false. Basic idea is I use the hash function to calculate the correct bucket. If there's just a single element, then I'm going to see if that's the correct one. Otherwise, I'm going to try to find it. The important thing is when we add something to the bucket, it's always the key value pair. It's not just the value, because then we cannot know what the correct key is. We need to have both the key value pair in there so that we can actually compare the keys. And in this case, I'm just looking for the correct key. If I find it, the element is part of the hash map, otherwise not. So return false. A similar thing can be done for the get function. So the get function is actually exactly the same structure. Only difference here being that we don't return true or false, but we return actually the value. And otherwise, we raise a key error. So key not found. So again, same idea. I get a key. I try to find, or I get the index, which is determined by the hash function. I go into that correct bucket. And if I find the corresponding key there, I return the value that belongs to the key value pair. That's it. And otherwise, I see key error because the key that you're looking for is not found. The put also works not too different, but here now, of course, we don't return, we create. So again, we can say, we can start in the same way. We need to calculate the correct index and we need to find the correct bucket, but this time we're not looking for something, we're appending something, or we are creating something. So we need to say here for I key value and enumerate this bucket. So we enumerate all the elements in the bucket. And the idea is if I already have the element in the bucket, I want to update it. If I don't have the element in the bucket, I need to create it. So I need to append it. How do we do that? We can use a fancy thing in Python called for else. I have a video on it. If you don't know the feature, this is quite interesting. If you break out of a loop, if you break out of a full loop in Python, you just break out of it. But if you don't break out of it, if you leave it without breaking out of it, you can go into an else branch. This is a feature of the language. So I'm going to show this here in a second. If the key is equal to the key, we can update the value of this key value pair. So we can say bucket I. So bucket at the position that we're at is going to be equal to key value. So to the new key value pair. The key is going to be the same, obviously, since we have this if statement, but the value is going to be whatever we pass here. So if it already exists, go there, change it. Otherwise, or maybe, not maybe, what we're going to do here now is we're going to break out of the loop, and we're going to append here an else branch. And in this else branch, we're going to say bucket append key value. So for those of you who don't know this feature of the Python language, this means that we're only going to get into this else branch if we leave the for loop without breaking. So if I go through all the elements here and I don't get to a break statement, then I'm going to go into an else branch or into the else branch. If I break out of the loop, I'm not going to go into the else branch, which means basically if there is no key, or if this key doesn't already exist in the hash map, then I'm going to just append it. Otherwise, I'm going to update it and break out of the loop. That's the idea. And of course, don't forget, if you add a new element, self.size has to increase to guarantee that we can do this here in constant time, because otherwise I have to iterate and count. And if I always just update this, I just have to look it up. All right. For removing it's now basically the same as getting, but we need to delete the element if we find it. So I'm gonna just copy the code of the get method here, and we're gonna say index bucket again. If you find the key, what we're going to do is we're going to delete, or actually before I do that, I need to be able to say which bucket element I want to delete. So again, I, and then this in enumerate bucket. And this allows me to say, okay, I'm in this position or at this position where I find the key, and I'm going to say delete bucket this position. Self size is obviously going to decrease by 1. And the important thing again, I want to break out of the loop. If I don't break out of the loop for some reason, it means that I don't find the key. So I raise a key error. So I remove the key from the bucket, and if I don't find it, if I don't ever get to this section here, it means the key doesn't exist, so I raise a key error. All right, so that's remove, that's the get, that's the put, and these are now not too difficult. All we have to do here is a simple list comprehension, because I just have to say k, so the key, for bucket in self buckets for, and then key, and you can say value or just placeholder in buckets. So this says go through all the buckets, get all the key value pairs, and give me all the keys. I can copy that, I can paste it down here, replace this by v, make this a placeholder, make this a v, and I can also then copy paste this. And here I want to return both key and value for bucket, key value in bucket. And that's basically it. Now let us talk again about the runtime complexities. So for this one, obviously I don't think we need to talk too much about this constant. I just have to look up the value. Regardless of the size, this is going to take the same amount of time. Constant, always. Contains now, and actually this belongs now, or this is now true for contains, for put, for get, and for remove. They all have, they all have linear runtime complexity in the worst case, because of the thing that I explained here with the, all of them could end up in the same bucket if you have a bad hash function or just very bad luck. But otherwise, you're going to have a good distribution. And because of that good distribution, on average, you're going to get constant runtime complexity. So for all of these, we have an average of O of 1 constant time, but a worst case of O of n linear time. And this depends on the quality of the hash function. We can copy this and we can paste this above all these functions. Every time we have to go to a bucket and find the correct slot that is worst case linear and average case constant. What we should say here, and by the way, this also, or actually for this, let me just think about this. We go through all the buckets. No, this actually has linear runtime complexity because we have to go through all the buckets, all the elements. So these three are linear every single time. This is not about worst case. This is also about best case and average case. We have to go through all the elements, all the key value pairs. Otherwise, we can't do that. So this is linear. And the interesting thing now is I always say here constant. And it's true, it's like constant in terms of n. So it doesn't matter how many elements, how many key value pairs I have. On average, it should be constant. But it's not entirely true because what you see here is we iterate over the characters of the string. So technically speaking, this function here is O of k, you could say. So linear in key length, which means that the longer your key is, the larger the effort or the more effort this function will have. But usually you don't use like extremely long keys, so you can ignore this. We could say practically speaking, we have O of 1 if we don't consider the key length. But if you want to be precise about this, the key length, the amount of characters in the key influence the runtime complexity of the hash function. And since we use the hash function in every single function here, we should say it's average O of k if you want to be precise, but O of 1 is fine. So constant time. All right, so let's play around with this. Let's say if name is equal to main, what I'm going to do here is I'm going to say hash map is equal to hash map. And now I can put some stuff into there. So I can say hash map append, or not append, sorry, put. And I can do stuff like name, Mike. And I can say age 30. And I can say job programmer, and so on. And what I can do then is I can say print hashmap dot items. And I have a problem here. Capacity, of course, yes. Sorry, let's go with 32. Orc, where did I use orc? Oh, sorry, ort, ordinal. So ASCII code, ORD. What else? List indices must be integers or slices. Yeah, sorry. We need to also, of course, return the hash result. If we don't do that, we know what the index is, but we don't actually return it. There you go. Now it works. So we have name, Mike, job programmer, age 30, and we can also see what the internal structure looks like. So I can say hash map and then buckets. And you can see in this case, I am quite lucky, or actually not lucky, this is to be expected, but I have a separate bucket for each of them. Now, the more values I add here, the more overlap I will have. So the more I will get into buckets that have multiple elements, especially because I only have 32 buckets. So at the latest point when I have like 33 elements, I'm going to have buckets that have more than just one item, but probably before that. So to show you how this works, or to see how good my hash function is, what I'm going to do now is the following. I'm going to say import UUID, which is a Python package or Python module that allows me to create these unique identifiers, which are just strings. And I'm going to say import matplotlib.pyplot SPLT. This is now no longer a tutorial about the data structure, just showing you how well it works. What I'm going to do here now is I'm going to say I want to have a hash map. This hash map should have a capacity of 100, so 100 buckets. And I'm going to say now for placeholder in range, and I'm going to use 1,000,000 elements here. So I'm going to add 1,000,000 different keys to this hash map. And I'm going to say hash map put UUID 4. So this is just a long string and probably unique, most likely. And the value doesn't really matter. I'm just always going to add the same value. But I'm going to place these different identifiers into the hash map as keys. And we're going to see how well they are distributed. If I have a bad hash function, this is not going to be evenly distributed. If I have a good hash function, it should be like pretty similar. So I'm going to say here x is equal to an empty list, y is equal to an empty list, and then I'm going to say for I bucket in enumerate hash map dot buckets. And here now I'm going to say x append I, just so I have the bucket number, and y append the length of the bucket. So how long is the bucket I? So that I have the lengths of the buckets, I want to plot them as bar plots. So I'm going to say plt bar xy plt show. And when I run this, this is going to probably take some time here. Maybe I should do it with less so that we don't have to wait too long. Let me just cut this off. Let's go with 5 here and 1 0 less. Actually, it's still running, right? Can I not? Oh, there you go. So this shouldn't take forever. But basically what I'm doing is I'm going through all the buckets, through all the 100 buckets, and plotting how long they are. So how many elements of the ones of the 500,000 in this case that I added end up in this bucket, and how many of them end up in the next bucket. And if I have like roughly the same height for each bar, this signals that I have an even distribution with my hash function. So I don't know what's happening here. Let me just run this maybe with even less, just to see if it works. Okay, so this was not representative because I didn't use a large number of values, but there is something in statistics called the law of large numbers, which means that the more elements you have, like the larger the numbers, the more you're going to approach, the more you're going to converge to the expected thing. So I think that with this hash function here, the more values I have, the more they're going to be evenly distributed. So actually this is not what I wanted to do. Let me add a 0 here and see if it gets better over time. But you see that the distribution of the bucket lengths, or the different bucket lengths, are not too different, which means that the hash function is decent. Because there's no bucket that's like super small or super large. It looks like they have a somewhat even distribution. So the runtime complexity here, yeah, I mean, it depends, because of course when we have the size limited, we probably have linear runtime complexity divided by something, which is still linear. But if you have enough capacity, you should have constant runtime complexity. So if I make this 1,000, It should get better. It should also be faster because I have more buckets and I have to do less of the searching, of the linear search. But yeah, this is fundamentally how you build a hash map in Python from scratch. We talked about the runtime complexity. I think this is a very important data structure, a very useful data structure. Also, if you do lead code challenges, oftentimes a useful data structure. Of course, in Python, you're going to use the dictionary usually. So just dict to create an empty dictionary, or if you want to initialize it right away here, key value. This is what we usually are going to do, but that's basically behind the scenes just a hash map. So yeah. Alright, so we're going to implement a binary search tree from scratch in Python today, and as always I want to start by taking a brief look at the theory, and then we're going to get into the coding. For this I'm going to use my favorite visualization tool, MyPaint, and I'm going to keep it simple here. The basic idea of a binary search tree is that we have a root node and we have left and right child nodes, and these can again have left and right child nodes. They don't have to have a child, so they can also point to none, which in terms of visualization, we would just not draw this connection. They can also have just one child node, so something like this is also possible. All of this is still a binary tree. Now, this is a binary tree in general. This is not necessarily a binary search tree now. A binary search tree also has the property that every key to the left of a node has a smaller key than the key of the node, and every key on the right of a node is larger. So basically, if I have something like 10 here as my key, it means that on the left side here, I can only have key values that are less than 10. So for example, I could have 7 here, and I could have then again here, we have the left node has to have a smaller key than this. So I can do something like maybe 2. Then on the right side, it has to be larger. So I could do something like 9. Then here it has to be larger again. So it could be something like 4. And the important thing is, of course, everything on the left has to be less than 7. So I cannot go ahead and do something like 20 here. That would not be a binary search tree. It means that everything to the left of 10, every single node here, all of this here, has to be less than 10. And on the right side, it's the opposite. So here I could have something like 20, and then here again, we have the same idea. I can have something less, or I have to have something less than 20, but it still has to be larger than 10. So for example, it would be 15. That's the basic idea of a binary search tree. Now, some terminology here. These nodes that don't have any children, we call them leaf nodes. So these are nodes that don't have any additional branches going down, not a single one. And this node at the top we call the root node. So that's the starting node of our binary tree. Now, a binary tree in and of itself is not very complicated to understand. The interesting part is some of the operations. Now, searching a value in a binary tree is actually also quite straightforward. So the basic idea is, let's add a couple of values here. So this could be 4. Actually, let's make this 5. This could be 4. No, actually, let's make this 3, and then, doesn't work. Let's do 6. Then let's do 5. No, still doesn't work. Let's do 4 would work, right? Yeah, 5 and 3. There you go. So let's say this is my binary search tree. In order to find a value now, for example, let's say I'm looking for the value 6. How do I find the value 6? Well, I look at the root node, and then I say, okay, is 6 less than or greater than 10? And of course, it's less than, so I go to the left. Now I have 7. Is 6 less than or greater than 7? It's less than 7. Okay, go to the left. Now, is 6 greater than or less than 2? It's greater than 2. Okay, so let's go right. And here I have 6 now, so I found the value. Because of that, it's not that difficult to find values. You just have to look at the current value and then go left, right accordingly until you get there. Now, of course, if I look for a value that doesn't exist, like 8, for example, how does this work? I go left because 8 is less than 10. I go right because 8 is greater than 7. I try to go left because 8 is less than 9, but I see there is nothing here. And because of that, I conclude 8 doesn't exist in my binary search tree. Now, the keys are used for navigation. What you can do in a binary search tree node is you can also add a value. So for the data structure, we're going to see that. I'm going to have a class here, node, and this node will have a left child, it will have a right child, it will have a key, which is the value that you see here, but it can also carry any information. So I can also have a value here. And the interesting thing about this is that with a somewhat balanced binary search tree, I will be able to find things quite quickly, because we're going to talk about the runtime complexity in more detail here, but the basic idea is if I have a tree that is somewhat balanced, now this one is not very balanced, but balanced means I have a pretty, you could say, symmetric tree maybe, where it looks somewhat like this. Most of the values are kind of on the same line. Most of the leaf nodes are kind of the same line. I don't need a lot of steps to get to any value. So if you consider this here, we have 3 steps maximum to get to any value. I have to go this, and this level. So to find a value. So we call this O of H, runtime complexity, where H is the height of the tree. You could say it like this, or you could say O of log n, because it's the logarithm base 2 of n. That is the height of the tree if it is balanced. Now, it's not really like this in the worst case, so that is the average case runtime complexity. In the worst case, a binary search tree could actually degenerate into a linked list, because if I have, for example, 5 as a value, and then I insert 6 as a value, and then I insert 10 as a value, and then I insert 20 as a value, and then I insert 30 as a value, you can see that I never go left because I'm always adding larger values. And because of that, I'm going right, and this is now just a linked list because it's just pointing to the next node in the list. But we're going to talk about this when we get to insertion deletion. We're going to need myPaint again. But for now, that's enough. We're going to code the data structure. We're going to code some basic functionality, and then we're going to discuss the insert, search, and deletion function again when we get to them. So let us get started by creating a Python file, binary search tree py, and let's maximize this. Let's zoom in a little bit. Let's call the first class node. The node class is something that we use in a lot of data structures. And we're going to say here now that we want to have a key, and do we want to have value? Yeah, let's also, or actually, let's not set a value. Let's just say a key. We can set the value if we want to. And we want to say now that each node can have a left child node. By default, this is going to be none. Each node can also have a right child node, which is going to be none in the beginning. The key is going to be set to the key. The value is going to be none. You don't need a value if you don't want one. But the idea, again, is you want to use something like a binary tree to be fast at finding something because you have logarithmic runtime complexity on average. And because of that, it makes sense when you find something to not just find the key, but also the value behind it. So it makes sense to have something there. And another thing that we're going to keep track of here, because it makes things a lot easier, is we're going to say self.parent. So instead of just having left and right, we also want to have a reference to the parent, so that each node here doesn't just have a pointer to the left element and to the right element. Now I'm using my mouse. But it also has a pointer to its parent node. That's going to be important, especially for deletion. It's going to make things easier. But that's the basic node class. And of course, for the representation, we're going to just implement the dunder wrapper. And here we're going to say now, we want to return an f string containing self.key and self.value. That's that. So that's the basic node class. And now we're going to implement the tree itself. We're going to say class binary search tree. It's also going to have a constructor. And this constructor is not going to take any arguments. We're just going to say self.root is going to be equal to none. So we have an empty tree. We have no root node. And that's it. Now, what we're going to do here now first is we're going to again define the signatures of the functions or of the method. So we're going to implement a contains method, which is basically going to be a search. We're going to see if something exists in in the binary tree. So I'm going to say here contains self, and we need also a value, or actually a key. We're always looking for the key, even if we're interested in the value. We don't search by value, we search by key. And then we're also going to use a couple of other dunders. We're going to use the iter dunder, which is quite interesting. This is basically what allows you, if you have, let's say we have some tree. So let's say I define a tree equals binary search tree, and then I can do for I in tree. What happens when I do for I in tree is defined by this iter dunder. So that is basically what allows me to iterate. And we're going to have 3 different traversal types, so we can choose from that. But for now, I'm going to just pass. Then we're going to also say representation. What's going to be the representation of the tree? It's going to be just whatever the traversal returns. But for now, again, we're passing. Then, of course, one of the most important functions is going to be the insert method. So it's going to take, oh, by the way, we need self here as well. The insert, we're going to insert a key and a value. We're also going to have a search method. So the search method is going to allow us to find the value for a given key, or to find a node. We're going to get the full node, not just the value. And then we're going to also have the delete method. This is going to work with a key as well. And then we're going to use traverse as well. Traverse is going to be a method that allows us to traverse the tree in different orders. So we're going to say order is going to also be a parameter here. And besides that, we're going to have a couple of private helper functions. I'm going to define them here as well, just so we know that they're going to be necessary. Because what we're going to do with the delete function or method is we're going to first use the search method to find a node, and then we're going to just delete it. So we're going to have a helper function, which we're going to call underscore delete. And that is going to be called by our delete method here. Then we're also going to need 2 helper methods called successor and predecessor. I'm going to talk about them when we get to them. They're going to be important for the deletion process, or actually I think the predecessor is not going to be relevant, but we're still going to implement it just for the sake of completeness. So successor of a given node. Then also the predecessor. Again, I'm going to define these when we talk about them, when we get to them. And then we're going to define 3 traversal methods. So these are at least the 3 that are listed on Wikipedia. This is why I implemented them here. So we have in order traversal of the tree. And then we have also pre-order traversal. And we have post-order traversal. And that is going to be what we implement in this video today. So we have the constructor, we have the contains method, which is just going to be the search method. We have an iterator, we have a representation dunder, we have an insert function or method, we have a search method, we have a deletion method. We can traverse in different ways. So this method here, the traverse method, will just call these 3 helper methods here. And the delete method will call this method, and we'll also make use of the successor. And for the predecessor, I don't think that we have a use case. Let me just double check. I think it's just implemented for the sake of completeness. So you don't have to implement it if you don't want to, but we're going to do it in this video today. So let us get started with the with the easiest one. I think the easiest thing is to just search for a value. So to just see if it's contained in the tree. And for that, we're going to implement this basic logic that I talked about, going left and right until you find something. How do we do that? Let's assume that we have values in the tree, or that we also don't have values in the tree. What we're going to do is we're going to say the current node is going to be the starting node, so self.root. And now we're going to just go left or right, depending on what key we're looking for, until we get to the place where it should be. And if we don't find it there, if we find a none reference there, we're going to just say, okay, we don't have that, so we're going to just return none. We can also raise an exception if we want to, but we're going to just return none, and otherwise we're going to return the node. So we're going to basically say if the current node that we're looking at is none, or the key of the current node is equal to the key that we're looking for, if one of these two is the case, we just return the current node. Why do we do that in both cases? Because if the current node is none, so if we don't have, oh, by the way, we need to do this in a while loop, because we need to do it all the time until we find this base case. So this is a little bit like recursion, but it's in a loop, so it's iterating, but it returns the moment that you find a key or end up at none. So if you end up at none, you want to return the node anyways, because it's just going to be none. So you want to return none since you don't find anything. And otherwise, you want to return the node that you found as well, because it has the key that you're looking for. So that is the base case. This is the terminating case where we actually return the current node. Otherwise, what we want to do is, if the key is less than the key of the current node, now it's not going to be none anymore because that's already the first case. So if the current node exists and the key that we're looking for is less than the key of the current node, what we're going to do is we're going to check the left node. So we're going to say if the current node left reference is none, we're just going to return none, because what we're looking for should be at the left side, at the left child node. It's not there, so therefore, or not just it's not there, but it's a none reference, which means there is nowhere to go from here, so return none, we don't find a value. Otherwise, we're going to make a step and say current node is equal to current node dot left. And then we're going to check again for this in the next iteration. And otherwise, we're going to also say, so basically this is the remaining case, if the key is larger than the key of the current node, or actually is that, yeah, if the key is larger than the current node, then we're going to say if the current node dot right is none, return none, else current node is equal to current node right. So I always like to show this again visually, even though I think a lot of you guys probably already understand this. I want to make sure that everyone can follow the logic. The idea is we have a tree like this one here, and I'm looking for a value. I just go left, right, depending on if the key is larger than or less than the current key. And the moment I recognize that the key is the one I'm looking for, so when I'm, let's say, at this node and I'm looking for 2, I can just return this node. And if, for example, I'm looking for 3 now, I'm going to see, okay, 3, or actually 3 is not a good example. If I'm looking for 1 now, what I have to do is I have to go left, but there is nothing left, so I have a none value here. Because of that, I just return none, because it means I don't find the node that I'm looking for. So that's quite simple, actually. Now, the contains dunder is going to be quite simple, but it's actually going to be easier because we're not returning the node. So all I have to do here is I got to say current node is equal to self.root. And then while current node is not none, I go left and right, and then I just return true or false. So I say if the key that I'm looking for is less than the current node dot key, then I just go and say current node is equal to current node dot left. Since I don't need to return it, I can just jump immediately. And if it's none, I'm going to recognize it anyways. So then here, if the key is current node dot key, if it's larger than current node dot key, I'm going to say current node is equal to current node dot right. And if I find the key, I'm just going to return true. And if I get out of this loop without returning true, I just return false. So that's quite simple when it comes to contains. And the question now is, how do I get values into the binary search tree? How do I actually insert something? And the idea here is actually quite similar, because what we need to do is we need to go left and right until we find a position we want to insert a new node, or where we can find a node that already exists and update the value. But then we need to do some extra work. So we don't just have to navigate to the position, we actually have to create a new node there, or we have to update an existing node. So in the case of the insert method, we're going to distinguish between 2 cases. The first case is quite simple. We don't have a root node, so we don't have anything in the tree. If self.root is none, we're just going to create a new node and make it the root node. So we're going to say self.root is equal to node with key and, or actually just with key, and then we're going to say self.root.value is equal to value. And that's it. That's the insert if it's the first node to be ever inserted into this tree. Now, In the other case, I need to navigate to the position where the new node should be placed, or I have to navigate to the position where the existing node with this key could exist, and then I have to update the value. Now you can also implement this in a different way. If you try to insert something that already exists in the tree, you can also maybe say, okay, in this case just raise an exception because I don't want to allow for duplicate keys. We're going to just say, in this case, update the value of the existing node. So we're going to say now the root exists. So what we're going to do is we're going to play the game with the iteration again. We're going to say current node is equal to self.root. And then we're going to say while true. We're going to go left and right depending on where our key is. So we're going to say if the key that we're looking for or that we're trying to create is less than the key of the current node, we're going to do the following. If the current node has a left child node, so if current node dot left is, or actually let's do it the other way around. Let's say if the current node left does not exist, that means that now I have the position where I have to insert my node, because I am at a node where the key I'm trying to create is less than the key that the current node has, which means I have to go left, and there is nothing left, which means that I have to create my new node there. So if current node dot left is none, we're going to create a new node here. So we're going to say current node dot left is going to be a new node with the key current node dot left is going to be equal, or current node left dot value is going to be equal to the value. And then this new node that we created should point back to the current node as the parent. So we want to also say current node left parent is going to be equal to current node. So that is also an important reference. And then important, we want to also break out of the loop. So we want to say break. Otherwise, if I want to go to the left, but there already is a node there, we're going to say current node dot left, or sorry, current node is equal to current node dot left. So that's the case for the key being smaller than the node's key. Otherwise, if the key is larger than the current node dot key, then we can just copy all of this here and replace left with right. So I'm just going to use here substitution. Left is going to be replaced by right. And that's now the difference here, because now same game, we want to go right. Right doesn't exist. Perfect. Create a new node, update the value, update the parent reference, break. Otherwise, go to the right. And then we have a final case, which is that the key is exactly what we're looking for or what we're trying to create. In this case, we just update the value of the current node. So current node value is equal to value, and break again. That is the insert logic. So again, what's the logic behind this visually here? I want to insert a new node. Let's say I want to insert the node 1, or actually let's go with, can I do 8? Let's do 8. How do I create a node 8 with a key 8? What I do is I go to 10. I see, okay, if I want to insert 8, I have to go to the left. Can I insert it here directly to the left? No, there already is a node here, so I cannot insert the node here because 7 already exists here. So go there, see that 7 is 7 and 8 is larger than 7, so I have to go to the right. Can I just create my key here? No, there exists a node, so it's not a none reference. It's 9. Okay, 8 is less than 9, so I would have to go to the left. Can I go to the left, or is it a none reference? No, there's nothing here. Perfect, create a new node. 8. If the node already exists, so if, for example, I wanted to insert 9, I can see that this here is 9, so all I can do is I can just update the value of 9. Value update, because 9 already exists. These are the two cases that we can have. All right, so that is not too difficult. The most fancy thing here is the delete method, which I think actually we're going to talk about next. Yeah, I want to talk about delete next, because delete has now 3 cases that we need to handle differently. And by the way, regarding the runtime complexities, I'm going to talk about them in the end. But for now, I just want to implement the functionality, and then we can talk about the complexity of that and the average case and worst case. But I want to talk about, or I want to implement the delete method first. And the delete method is interesting because we have basically three different cases, and these are the following. So I have a very simple case, the first case, where I'm deleting a leaf node. So let's say I have a tree like this. I have 10, then maybe I have 5, and then maybe I have 15 here, or actually let's go with 20 so I have more space. Then let's say I have maybe here 2, maybe I have 7 here, and then maybe I have 9 here, and maybe I have 12 here, and then I have 30, and then I have 22, 21, 23. I'm just adding a couple of notes here to also highlight the other examples. Let me delete all of this here. And then maybe we have 35, whatever. Deleting a leaf node is super simple because I just have to remove the node and that's it. So if I want to remove 2, if I want to remove 9, if I want to remove 21, 23, 35, all I have to do is super easy, cut the connection. So cut it in both directions. Remove the reference from 5 to 2 and remove the parent reference from 2 to 5. That's it. Done. That's the most simple case. The second case is I delete a node, with one child, exactly. So that would be, for example, 7. If I want to delete 7, because 7 only has a single child, that's super simple as well, because all I have to do is I have to delete 7 and I have to redirect the connection. So I cut the connection between 7 and 5 again. I cut the connection between 7 and 9 in both directions as well. And then I add a connection between 9 and 5. So I just replace the node I'm deleting with the only child node. I don't have to make a decision here. It's super simple. I just replace 7 with 9. So in this case, I just replace this node here with 9. Super simple as well. The third case is the only one that's kind of tricky. The third case is I delete a node with 2 child nodes. And in this case now I need to do the following. I need to replace the node I'm deleting with its successor. So that's a new term that we already talked about in terms of the function name. But a successor, the successor node, is the first node, or you could say the smallest node that has, or the node with the smallest key that's larger than the key I'm replacing. So in this case here, I'm replacing, let's say 20. 20 has 2 child nodes. In order to replace it, I go to the node that is the smallest node that is still larger than 20. And in this case, that's 21. So 21 is the successor of 20. Why? Because it's in the right tree, the leftmost node. Now, if 21 didn't exist, I would replace it with 22. That would be now the successor. So I'm replacing it with the smallest key that is still larger than the key I'm replacing. That is how you handle that. So in this case here, it would be remove 20, replace it with 21, and remove 21 from down here. In the other case, if I didn't have 21, I would say, so if this doesn't exist here, I would say remove 20 again. And now replace it with 22. And of course, what happens then is that I have to also shift this up. So that's that. So we want to replace everything. We want to replace the node that we're deleting, if it has 2 children, with its successor. Now, for the sake of completeness, we also talked about the predecessor. And the predecessor is the opposite. It's basically the largest node that's smaller than the node. So it would be, the predecessor of 10 would be 9 because it's the largest node that is still less than 10. So this is something that we're not going to use for anything, but just for the sake of completeness, we're going to implement this as well. But for the successor, it's the smallest node that's larger than the current node. So let's put all of this now into code. In our delete method, we're going to first find the node if it exists. So we're going to say node is equal to self.search key. And if the node is not found, so if node is none, we're going to raise a key error because we're trying to delete something that does not exist. Node with this key does not exist. And otherwise, we're going to call the helper method underscore delete onto the node. Actually, why is this key? It should be nodes. So we want to call this with a key, but that should actually delete a node object. So we actually want to work with a node, not with a key. So we find the node using the key, but then we want to actually delete the node itself. And what we're going to do now here is we're going to define these three cases. The first case is node is leaf node. The second case is node has one child node. And the third case is node has two child nodes. So if the node is a leaf node, how do we actually check for this? We say the node left is none and the node right is none. If that's the case, it's a leaf node because it doesn't have any children. And in this case, we're just going to check for the special case that the node that we're deleting is the root node. So if node.parent is none as well, we're just going to say self-root equals none. That's the special case. Otherwise, it's not the root node. So what we're going to do is we're going to say if we need to determine which node of the parent node this is. So let me show this visually again. I need to use my drawing tablet quite often here. If I have a node that I'm deleting, so let's say I have 10 here and I have 5 here and I have 20 here. Let's say I'm deleting 20. If I'm at node 20, I of course have to set the reference of the parent node. So in this case of 10, the right needs to point to none after this. But when I'm at 20, I don't know if 20 is the left or the right child of 10. I only know that if I'm looking at 10, because then I can see left and right. But if I'm looking at 20, 20 just tells me my parent is 10. It doesn't tell me I'm the right child of 10. And because of that, we need to check for this. So we're going to say if node parent right is equal to node, then we're going to say the following. Node parent right is going to be none after this. Otherwise, node parent left is going to be none. And in any case, I'm going to say node parent is going to be equal to node left. No, actually, this doesn't make sense. Sorry, node parent is equal to none. Again, idea is I'm looking at the parent. I want to know, am I the parent's right child or am I the parent's left child? Depending on that, I'm going to set the respective reference of the parent to none because this node is now deleted. And of course, I also want to remove the reference from this node that I'm deleting to the parent. So I set this to none. The second case now is that I need to use an elif here because it needs to be still connected to the if statement. We're going to say if node left is none or node right is none. The reason I can do that here is because usually that would not be enough to check, but since I already have excluded the case that both are none, since I have the if statement here, if I get into this, one of them is none and exactly one of them is none. Because if both were none, it would get into the if, otherwise it gets to this checking here. So if still one of them is none, exactly one of them is none. So I can say that the child node, since there is only one, is going to be node.left if node.left is not none, else it's going to be node.right. So the node that is the child node of the node I'm trying to delete, there is exactly one, so I can determine if it's the left one or the right one, because one of them is none, the other one is not. And again, here I have the special case that the node I'm trying to delete here is the root node. So if node.parent is none, that basically means that the node is the root node, because the root node doesn't have a parent. In this case, I have to say that the child node's parent is going to be none as well. Because basically if I'm trying to delete, let's say I have 10, the root node, and let's say I have 20, the only child node of that, if I'm deleting the root, of course, that has to now point to none as the parent, because that is now the new root node. So I need to say that, first of all, the reference to the parent has to be set to none, but then also self.root needs to be that child node. Otherwise, I just have to do the following. I have to say again, if the node parent left, or we did right first last time, so let's do right again, is this node that I'm trying to remove, then I need to say the node parent right is equal to the node. Otherwise, node parent left is equal to node. And now we do the following. We say child node dot parent is equal to the node parent. This is clear. But then we also need to say that the node parent is equal to the node left is equal to the node right is equal to none. So this is just killing the node. I'm removing the node. The basic idea here being that my node that I'm trying to delete has a parent. Actually, sorry. I need to set this to child node. Okay, so my node that I'm trying to delete has a parent. So this node is either the right child or the left child of this parent. And what I want to do now is I want to redirect this reference, whatever it is, left or right, to the child node. Since I only have one node, I know which one to redirect it to. So again, maybe before I talk too much here without visualization, the idea is I have 10, 20, and 30, let's say. I'm deleting 20 now. So I need to redirect the reference here. It's the right one in this case. I need to redirect it to this child node. And then I also need to set the child node's parent reference to the parent that it was before. And then I need to cut all the connections. I need to cut this one. I need to cut this one in both directions. So all of this needs to be cutted. The reason we also set this one to none is because we don't want to check necessarily if it's the left or right node. I just set all of this to none. Parent, left, and right are set to none. That's definitely going to be true. And I redirect the connections here between parent and new child node. The last case I have here is that I have two child nodes. And this is now where the successor function or the successor method becomes relevant. So before we implement this branch, I'm going to say pass, and we're going to implement the successor method. It's actually not that difficult. Because think about it, I'm not sure, do I still have the drawing here? Yeah. Think about this. In order to find a successor of a node, all I have to do is I have to go right once, because remember, it has to be larger than the key of the node I'm currently at, but then it has to be the smallest possible value. So to find a successor, I go right once, and then I go left, 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 left until there's nothing there. So in order to find a successor, I say if node is none, I will raise a value error because cannot find successor of none. But otherwise, I'm going to say, actually, I don't need an else branch. I can just do it like this. If the node right is none, then I don't have a successor. So if there's not a single node that has a larger key than the current node, then I'm not able to find a successor. Otherwise, if there is a right node, I'm going to say current node is equal to that right node. So go right once, and then while we have current node dot left, so while that exists, say current node is equal to current node dot left, and in the end return the current node. So again, go right once and then go left all the time. This will inevitably lead to the successor. So if I look at 10 here, what's the successor of 10? Go right once and go left as long as you can. And of course, if I had, for example, 11 here and 15 here, then I would do the same thing. Go right once, left, left. If I'm looking at 22, go right once, left. and go left as much as you can. In this case, there's no room between 22 and 23 if you're using integers. But the idea is go right once to make sure it's larger than the current key, but then go left to get the smallest value possible. That is the successor. Now for the predecessor, it's actually basically the same thing in the other direction. So I can copy that, and the only thing I have to change here is I have to go left once, and then I have to go right all the time. And that's how I find the predecessor. So that's quite simple. And we said that if we want to delete a node with two child nodes, all we have to do is we have to find the successor. So I can say successor is equal to self._successor of the node I'm trying to delete. And then all I have to do is I have to say the node key is going to be equal to the successor key. The node value is going to be equal to the successor value. So I replace the key and the value of the current node with the key and the value of the successor. And of course, if you have other fields here that are relevant in terms of data, so something like, I don't know, some file pointer or something, anything that belongs to the content of the node, you want to copy it here, and afterwards you want to delete the successor. So basically what's going to happen here is, let's say I'm trying to delete 22. What I'm going to do is I'm going to delete the key and the value of 22. So whatever is in here, I'm going to wipe it clean. And the successor is 23. So what I'm going to do is I'm going to copy the value here, 23, and whatever the value is, like hello or something. And then I'm just going to delete 23. There you go. That's the basic idea. And since we have the delete method, this is going to be done properly. So if it's a leaf node, it's just going to delete it. If it has exactly one child, it's going to shift it properly, and it cannot have two children, because then I could go left one more time. And yeah, because basically if you try to delete the successor, it can either have one child, the right child, or it can have no child. So it's a leaf node. And that is our delete method. So we call it here, we find a node here with a search function, then we delete this node, and the deletion happens in these three cases. All right, so the last thing that we need to implement before we talk about the runtime complexities is the iteration, and of course also the representation, but the representation is just going to be a string version of the iteration. So let us implement the traversals. And we're going to actually do that here as generators, because what I want to do is I want to be able to iterate over it. And because of that, we're not going to return. We're not going to just print. We're going to actually yield. So we're going to yield from the traversal functions. So the in-order traversal is basically, you want to go through the left subtree first. You want to go then to the root node, and then you want to go to the right subtree. So let us see what this would look like in our example tree here. The in-order traversal is actually quite intuitive. Again, remember, we go left first, then root node, then right. And this basically means we go left, left. There you go. Then we go root node. So root node in this little subtree here is 5. Then we go right. So we go to the lowest level. Then here we only have a root node, so we print this. Then we go up, so we have left, root, right. This is left, root, right. Now, right here is again left, 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 root, right. Then root, since this is left. Then here again, left, root, right. And if you look at the numbers, that is why it's called in order, because we go 2, 5, 9, 10, 11, 12, 15, 22, 23, 30, 35. So we go in ascending order. This is just the ascending order. That's why it's called in-order traversal. Now the pre-order traversal is root node first, then left, then right. So it would be 10, 5, 2, 9, 22, 12, 11, 15, 30, 23, 35. Yeah, so that's the pre-order traversal. And the post-order traversal is now left, right, root. So we go first 2, then 9, then 5. So 2, 9, 5. Then we also don't go to 10 yet. We go 11, 15, 12. Then we go 23, 35, 30. Then we go 22, and then we go 10. So that's the last thing. The root node is always the last thing. And these are the three methods that we're going to implement now. So we're going to go into our code again. And here we actually need to change this now to accept the node argument because we're going to call this recursively. I'm going to explain here in a second why. The basic idea is I actually already said that while showing the visualization, but every node can be considered a subtree. So if I do the in-order traversal, we said we go left, root, right. We do that on for every node. So if we only have one node, that's the only thing that we can return. But otherwise, we can consider this to be left, this to be right, and this to be root. So first call is left, root, right. And since this is the first one here, I do the same thing. I have this subtree now, left, root, right. And in here, I do the same thing. So I do this, I do root, and then I do here again, left, root, right. And then within this tree again, left, root, right. So this is why we call this recursively. Now, there is a caveat to this because we're not actually returning, we're not just printing, we actually want to yield the values, we want to generate these values. Now, for those of you who don't know what generators are in Python, I'm going to briefly open up an interactive shell here to show you. Let's say I have a function gen, and this function just iterates for I in range 20. Now, I don't return these values, I don't print these values, I want to yield them, I want to generate them. So instead of printing them, I can just say yield I. Now, what does this do? What this does is when I create my generator object here, I can iterate over these values. I can get the next value. So I can use the next function onto my generator to get the next value from this loop. And I can also iterate over it. So I can say for x in my gen, and then I can just print x. And this will now no longer give me 0 and 1 because I already used those, but I will get 2, 3, 4, and so on up until 19. That's the idea of a generator. I generate values, I yield values. And we can also do that recursively. So what I do here is I say if the node is not none. What I do is I call this function recursively. So I say, or this method, self.inOrder traversal on node left. So we go again, left, root, right. That's the in-order traversal. So I also do that on right, but in between I also need to yield the node that I'm currently talking about. So the node that is currently my root node here. So I say yield, and then this node's key and this node's value. That is going to be my base yield case. However, I also want to yield whatever I get from here. So in order to yield everything I get from this call and everything I get from this call, we use the syntax yield from. So this basically yields whatever these functions yield, or methods. If you're confused by that, if you don't know what I'm talking about, you can watch a video on generators, you can watch a video on yield from. I do have videos on this on my channel, but I'm not going to explain generators now here in more detail. But that's the basic idea here. We want to yield the values in this order, and then I can just copy paste this to my other methods. So I can say, in this case, I keep everything the same, but for the pre-order traversal, I yield the node first, and then actually I need to change this then to pre-order traversal as well. And you need to consider, of course, this order of left, center, right is, of course, then also recursively applied within these function calls. So it's always this principle, the same thing that I showed you in my paint. And then for the post-order traversal, all I have to do is I have to change this to post order, and this needs to be yielded last. So these are the three traversals. And to actually do a traversal now, I need to call them. So I need to call them here in the traverse method. So we're going to say here, if order is equal to in order, then we're going to say yield from self dot in order traversal starting at the root node. Elif, the order is equal to pre-order, yield from pre-order traversal roots. Elif, the order is equal to post order. I'm gonna yield everything from the post order call. And if I get anything else, I can raise a value error unknown order. There you go. So that's how this works. And now finally, we can also implement the iter and the representation dunder. This is quite easy. All we're going to do for the iteration is we're going to say yield from, and then self.inOrder traversal is going to be our default of self.root. And then we're going to say yield, here actually not yield from, we're going to say for the representation, we're going to return the string version of the list version of whatever we get from the iterator. So, or not from the iterator, from the generator, self root. So we call the in order traversal onto root, we turn it into a list. You can turn a generator into a list. It will just generate all the values and store it in a list. And then we can turn that into a string and return this. So that is the implementation of our binary search tree. Now let us talk about the runtime complexities. We already talked about them in the beginning. The basic idea is when I have a tree, my average case runtime complexity and my worst case runtime complexity are different. Now if I start at the value 20 and I go left, right, and I append 10 and 30, and I do that in the perfect balanced way, 5, 15, and 25 and 35. If I do that like this all the time, I keep the balance by inserting the values in a specific way, then I will have a balanced tree, and the height of that tree will be the logarithm of n. So the height in this case will be the logarithm of n, base 2, and I will only have a very small number of levels compared to n. However, if I do it in an unintelligent way, so the same values inserted like this, 5, 10, 15, 20, 25, 30, 35, now the height of the tree is actually n. So I have as many levels as elements, which is not a good thing. So in this case, I actually end up with a linked list. And this is an actual case. This is a real case. It can happen. So that would be a worst case runtime complexity of n for basically anything. For searching, because if I want to find the value 35, I have to go through all n elements. For inserting, if I want to insert 36, for example, I have to go all the way to the end. For deleting, if I want to delete 35, I have to go all the way to the end. So in the worst case, I have an O of n linear runtime complexity. If I want to do this in a balanced tree, so in the average case, if I consider the average case to be the tree is somewhat balanced and I have a height which is logarithmic in terms of n, that would mean that I only have to go a logarithm of n levels low. So that's a very good runtime complexity because all I have to do now is, in this case, I have 1, 2, 3, 4, 5, 6, 7 elements, and I only have 2 levels, which means that I only have to make 2 decisions to get to any node. If I want to delete 35, I go right, right. If I want to find 15, I go left, right. I only have to go a maximum of 2 actions for 7 elements. That's the idea behind this being an average runtime complexity. So in the code, I'm not going to now add all the comments here, but basically for all these things here, except for the iteration and the traversal. The traversal is always going to be linear because you have to go through all the elements. So actually, let me add some comments here. This is always going to be O of n. This is always going to be O of n because in order to go through all the elements, you have to go through all the elements. So this is going to have a linear runtime complexity. This is going to have O on n in worst case and O of log n in the average case. And it will have O of h, so O of height, always. And I can copy this now and put this over insert. I can put this over search. I can put this over delete. Traverse is going to be linear. And these are now just the helper methods. And for the successor, of course, you could also argue in order to find a successor, you have to go a certain number of steps on average, or in the worst case, but these are now the methods. So linear runtime complexity, no matter what for the traversals. Otherwise, average case is log n, best case, not best case, worst case is linear, and it's always linear in terms of height, but the height depends on how you structure the tree. So that's the implementation. Now let us move on to the actual experimentation. So let's actually see if this produces some problems. If name is equal to main. And now what I'm going to do is I'm going to reconstruct the tree that we're constantly talking about here. So this tree up here. So we insert 10, 5, 22, 2, 9. So let's say BST is equal to binary search tree. And now BST insert. And I want to insert 10 in the beginning. And let's say the value is always going to be just hello or something. You can use different values if you want to. But we're going to say 10, 5, 22, 2, 9. So 10, 5, 22, 2, 9. And then we have 12, 30, 11, 15, 12, 30, 11, 15. And then we have 30, 23, 35. Was it 20? Not sure. No, 30, sorry. 30, 23, 35. All right, so that's the tree that we already have in our MyPaint sketch, and now we can actually see what happens if I say print, or actually for the traversal, this is also an iterator. Yeah, so let's say for I in BST traverse in order, what does this look like? Print I. We should see all the numbers in ascending order. And in this case, I get a problem because in line 11, I have some issue with the representation. That is because I have an extra curly bracket here. Now let's run this and I can see 2, 5, 9, 10, 11, 12, 15, 22, 23, 30, 35. So that works perfectly. Now let's go for the pre-order. We talked about what this should look like. So let's actually move this to the left. Let's move this to the right. And we can see now what it does is it says first the root node 10, then 5, then 2, 9. So we have the structure of first the root node, then the left, but of the left, of course, also the first root node. So we go 10, then we go left, but we don't go left all the way. We go first the root node again, 2, 9, then we go right, first the root node again, 22, 12, and then 11, 15, 30, 23, 35. And for the post-order traversal, it's going to be the same post-order. It's going to be the root node last. So 10 is the last, as you can see. And you can go through it and see that it works as well. So the interesting thing would be what happens if I now delete something. Now, if I delete, let's say, what would be an interesting thing to delete? Let's start with the base case. What happens if I delete 9, which is a leaf node? that shouldn't be too difficult. And now actually, let's go with pre-order traversal to see if this still works. If I delete 9, what happens is I get still 10, 5, 2. I don't get 9 because 9 is deleted, but the rest of the structure works. Perfect. Now let us delete not 9, but something with 1 child. We don't actually have something with 1 child. So actually let's append another node, bst insert, and let's insert 1. The reason for that is I want to have something that I can check the case with. So I would have 1 here. And in this case, let's also delete 1 again. And yeah, basically nothing changes. Or actually, sorry, I didn't want to delete 1. I wanted to delete 2. Because now 1 should replace 2. Wrong key. There you go. So now I have 10, 5, 1, 9. Because 2 is no longer there. So this works as well. And now let us go ahead and remove 22. What should happen? Remember, we go right and we should replace it with its successor. It should be replaced by 23. So we should see 10, 5, 2, 9, then 23. So let's remove 22. And we have a problem. So there is a problem with the implementation. Let's fix that. Okay, I found a mistake. We should call the underscore delete method here when we delete the successor and not the delete method itself, because this one here takes a key and this one takes a node. So we actually want to delete the successor node that we find here, which means we want to call underscore delete successor and not delete successor. This should resolve the issue. So let's put this here again. Let's run this. And now we can see what happens when we remove 22. 23 moves up. So we have 10, 5, 2, 9, and then we have 23. So of course this doesn't exist anymore. So 22 was replaced by 23, and then we go on with 12, 11, 15, and then 30, 35, because we don't have 23 here anymore. So that works perfectly fine. And we can also print the tree itself, which is just going to give us a list of the pre-order elements here, or not pre-order, in order elements, in order sorted elements here. And besides that, I think we tested everything. I mean, the search, we could try the search. Print bst search, and then give me the value of 30. In this case, it's just going to give me the node with 30 hello. So yeah, this is how you can implement a binary search tree from scratch in Python. Alright, so we're going to implement the heap data structure from scratch in Python today, and as always I want to start by giving you guys a little bit of a theoretical understanding of the data structure before we get into coding. And a heap is a tree-based data structure similar to the binary search trees that we talked about last time, but it has different properties, different operations, and also different use cases. So in a heap, first of all, we have two different types. We have a min heap or a max heap, and depending on that, the order is reversed. But basically, we have a top element, which is either the minimum or the maximum of the data structure. So for example, if it's 10, all the values below 10, so all the values in the nodes below this top node here in a min heap would be larger than 10. So for example, they could be something like 20, 30, 40, 60, 50, 35, whatever, it doesn't really matter, but all these values are larger than 10. So the minimum element is always at the top. And this is, by the way, true. If this is a heap, if this is a min heap, then all the subtrees here are also min heaps. So you can see that 30 is smaller than 50 and 35, and 20 is smaller than 40 and 60. So all the subtrees in a heap are also heaps. And if it's a max heap, it's the other way around. So it would be, for example, 5, 3, 2, 1. I mean, if we allow for duplicate elements, we could also have 3 here. But we basically have the structure that the topmost element of each heap, so also of the sub heaps here, has to be either the largest or the smallest element. So it's not like in a binary search tree where everything to the left is less than and everything to the right is greater than the value, but everything below this node has to be larger or smaller than the value that we're talking about, depending on whether it's a min heap or a max heap. And this is very useful to implement a data type, an abstract data type, which is called the priority queue. Now, the priority queue itself is not a data structure, so it is a thing, an abstract data type that can be implemented very efficiently using a heap. So basically the element with the highest priority or with the lowest priority would be at the top, and then we could just get the next most important element. And for this, we basically have two operations that are important. For example, if I have now here again 20 and 30, and then maybe I have 25 and 40, and then maybe I have 50 and 32 or something like this. How a heap works, how a min heap works in this case, is I can extract, this is the method, I can extract the minimum of this min heap. So I would get 10 out of the heap. I would process it if it's a priority queue, for example. And then what happens is I remove this node. So I don't have the root node anymore. I don't have the top node anymore. So what do I do in a heap? What I do is I take the last element. We're going to talk about what last means in a second here. I'm going to show you how this works in terms of calculation, because we're actually basing all of this around an array full of values. And the indices determine which node or which value is the child of which other value. We're going to talk about this here in a second. But basically what we do is we remove the top node, then we take the last node, we put it at the top. So we basically take the last node here, we remove it from the end, we put it at the top, and now this is of course an invalid heap. This is no longer a min heap. And what we do is we do a so-called sift down operation, which means that we look at the two child nodes and we determine which one is the smallest. So in this case, 20 is the smallest of these three. So we swap the position with 20. And in this case, what would happen is we would get 20 up here and 32 down here. And then we look again, okay, what's the smallest one of these three? We see it's 25. So we replace 25 with 32 and vice versa. And now this is a valid min heap again. Now, theoretically, if I had some elements down here like 500, let's choose some big numbers, 600, then I would make the comparison and see that this is already the smallest element, so I'm done. So I don't have to go down. I mean, actually, this wouldn't be possible here because we would have some values here, but the idea is that you stop when you have when you are already the smallest value. That's the basic idea. We're going to talk about this more when we implement it. The second idea is what happens when I add a new element. What happens when I add a new element? Let's say, for example, here I have 36 now again, or something like this. And now I add a new element. What happens is I append it to the heap just at the next free slot. So you can consider the slots to be like this. We have the first one, the second one, the third one, 4, 5, 6, 7, 8, 9, 10. So this is how it's ordered. I'm going to talk about this here, as I said, in a second when we talk about how this works as an array. But basically you input some element. Let's say, for example, I input the element 23. Or actually, let's go with something that will end up at the top. Let's go with 5. And what I do now is I sift up the element. So now we're not doing a sift down operation. We're doing a sift up operation, also called a swim operation. So we're comparing with the parent node which one is larger, which one is smaller, and then we're replacing them if necessary. So in this case, 5, of course, is smaller than 32, so we replace them. 5 is also smaller than 25, so we swap them. And 5 is also smaller than 20, so we swap them as well. And now we have a valid min heap again. That's the idea. So for extraction, we take the top, we replace it with the last element, we sift down. For deletion, for insertion, we insert at the end, and then we just sift up until we are at the proper position. Now, how does this work as an array? So how this works as an array is that I have an array with all these values, and the indices are calculated as follows. So the root element is always, or the top element is always the first one. So I have 5. Now the two children of 5 are 20 and 30. So they are the next elements. And the children of 20 now are the next elements. So I would have 25, 40. So these are the children of 20. These are the children of 5. Now the children of 30 are the next in the list. So they would be, this is 50, right? So we would have 50, 36. And then we have the children. So these are the children of 30. And now we have next the children of 25. The children of 25 is just 32. And that's it. So that is our array. Now, instead of just understanding this visually, we can also put this into a formula. So the parent, or let's start with the left. The left child of a node is the same as saying 2 times the index of the node plus 1. And the right child is 2 times the index of the node plus 2. So if you consider that to be index 0, where do I find the left child of 5? 2 times 0 plus 1, 1. Okay, where do I find the right child? 0 plus 2, 2. Okay, where do I find the right child of this? It's index 2, so it's 2 times 2, which is 4, plus 2, which is 6. So 3, 4, 5, 6. There you go. 36 is the right child of 30, as you can see. This is how you calculate that. The other way around, we could say that the parent of a node, if we want to know that, is the index of the node that we're looking at right now, minus 1, floor divided by 2, if it's not 0. So if the index is not 0. Because then, of course, we don't have a parent node for the first node. But basically, if I want to know, okay, what's the parent node of 50? This is index 5. So what I do is I say 4 divided by 2, 2. So the parent of 50 is 30. That is how we do that. So all of this can be represented in an array, in a simple list. We don't need to work with nodes or anything like that. We can just do index calculations. So that's it for now. Let's get started with the coding, and then we can go and discuss more details as we implement the functionality. So let us go to the current directory, and here now we're going to create a new file called heap.py. So now we're actually going to have just the heap class. We're not going to have nodes. I think this is the first data structure where this is the case. So we're going to implement a min heap now. Again, I'm not sure if I talked about this, but the max heap would be the other way around. So we would have 50 at the top, and then we would have values that are less than 50 at the bottom, or below 50. All right, so min heap. Let us get started with the initialization. The initialization is going to be, so the constructor is going to be just the heap is going to be an empty list. And then we're going to implement the following functions. We're going to have a length function, so a dunder method. We're going to have a representation dunder. We're going to have the method insert, where we're going to be able to insert key and value. By the way, this is something that I didn't mention. All of this that I showed you here is just regarding the key. Every element here that we have can also contain an arbitrary amount of payload or value, we can say. So 5, 20, and so on, these are just the values for the heap to be able to structure the elements, but each of these could have a package attached to them. So here we could have some string hello, for example, attached as a value to this thing. And here we could have some value world attached to this thing. So it doesn't have to be just a value, it can also contain a payload. Which is why we are going to insert key and value, we're going to insert tuples, and we're still going to focus only on the key for the whole operation, but we're going to be able to do that. Then we're going to have the operation peak minimum, which is going to be the same as extracting, but we're not going to actually remove it, so we're just going to show it. So peak min key, or actually, sorry, not key. peek min, and this is going to return the key value pair. Then extract min, which is going to actually do the extraction. It's going to actually remove it from the heap, and then we have to do the sift up, sift down operation. Actually, not sift up. And then we're also going to implement the following methods. We're going to implement heapify. We're going to implement melt, which is going to be combining the heap with another heap. So we're going to have here other heap as a parameter. And here we're going to actually pass a list. So elements. To summarize this, heapify will mean we get a list of elements, doesn't have to be sorted, doesn't have to be structured in a certain way, and we take that and structure it so that it becomes a heap, so that we actually get this array structure here that we talked about. And then we're going to have the helper methods that we talked about. We're going to have a parent method, which is going to take an index as input and return the parent index. We're going to have the left helper method, which is going to take an index and give the left child of this index. And we're going to have the right helper method, which is going to do the same thing for the right child. And then the most important methods here are going to be sift up, sift down. So sift up a specific index and sift down a specific index, which are also called, as I said, maybe as a comment here, this is called the swim operation and this is called the sync operation. And as always, don't worry, we're going to talk about the runtime complexities of all these things at the end, but I want to implement them first before we talk about the complexities so you understand how this works. So for the length, it's quite simple. We just return the length of self heap. That's not too complicated. For the representation, we can also just return the string version of the list. So this is quite easy. We just show the list and that's it. Show the heap and then you can look at the list. If you want to visualize this as a tree, go ahead and implement the logic to do that. I'm just going to print the heap. And now let us start with the insert method, because that's actually quite simple, even though the logic that makes it more difficult is going to be inside of these methods here. So for the deletion, for the insertion. But remember, all we have to do to insert a new element in a heap is we have to add it to the end and we have to then sift it up. So we're going to say here self.heap append key value and then just self.heap sift, sorry, not self.heap, self.sift up this index, which is going to be the length of self.heap minus 1. So remember, for the insertion, all we need to do is append the new element here, and then it's going to not necessarily be at the correct position, sift it up the tree wherever it has to go. And this is always going to be the last element, so length minus 1 is perfect to index it. So the logic will be implemented here in sift up. Peak minimum is also quite simple functionality. All we have to do is we have to say if self.heap, or actually if not self.heap. So if the heap is empty, if we don't have elements, we're going to raise, let's do an index error, because we're going to say empty heap. And otherwise, we just want to get the first element. So just return self.heap 0. That's going to be the minimum element. It's always going to be the root. It's always going to be the top, the first element. Because of that, just return it without doing anything else. For the extract minimum, we can start in the same way, but we have to do it differently because now we're no longer just showing the element. We're not just returning it. We actually have to remove it. We have to extract it from the heap. So we can say min value or min element is equal to self.heap 0. That's the same as before. But instead of just returning it, we now say that the last element of the heap is the self heap, and now the index is again, or actually we can use the pop function here. So either you can access it in the same way by saying length heap -1, or you can just use pop. This gives you the last element, so it pops out the last element. If you do it with the index, you have to remove it with the delete keyword or with the del keyword. But with a pop function, you just pop out the last element, you take it, and what we're going to do now is we're going to say if self dot, or actually we don't need to do that because we already checked for that. Or no, we actually have to do that because by popping the element, it could end up being an empty list. So for example, if I have just one element in the heap, which is 10, if I pop it, I could have now an empty list, which means that I need to do it differently. Otherwise, I just remove it, right? And I don't need to do anything. But if I have elements left, so if there is something left in the heap, I need to say that the heap at the first position, the root element, now becomes the last element. And then I want to sift it down. So self.sift down, and then index 0. And in the end, of course, the most important thing, we're going to return the element which we extracted. So again, visually, what are we doing here? We're saying, okay, I'm removing 5 from the list. So from the heap, what am I doing? I'm removing this node and I'm returning it. So here, return 5. But what I need to do now to restore the heap is I take the last element, so 32, and I put it at the top, 32, and then I sift it down. So I compare this again. Okay, this is now 32, this is now 20. Then I replace it also here again. This is now 25, and this is now 32. There you go, heap is restored. So that is what we're going to do. So we're sifting down the element. Insert and extract are going to use that, so let us go ahead and implement these now. But before we do that, let us briefly implement here the parent left and right formulas. These are exactly what I showed you here. So right is 2 times index plus 1, right is 2 times index plus 2, left is 2 times index plus 1, and parent is index minus 1 divided by 2. Of course, there are some conditions here. So for example, maybe the node doesn't have a right child. In this case, we would go out of bounds, and we don't want to do that. So we need to return, in this case, none. So we are going to say here for the parent, return index plus 1 floor divided by 2 if the index is not 0. Otherwise, we don't have a parent because that's our root element or top element. For the left, we say return, or actually, let's say left is equal to 2 times index plus 1, which is the formula that we talked about. And now we're going to say return left if left is in the bounds. So if left is less than the length of the heap, otherwise return none. And the same goes for right, just with a different formula. We're going to say here right, and then we're going to say return right, and we're going to say plus 2. So that's that. Now let us implement the sift up. The sift up is just comparing to the parent and moving up if the parent is, if the position is not correct. So if the parent is small, if the parent is larger than me, then I have to move up because I belong further up in the hierarchy to make this a valid heap. So we're going to say here the parent index for the current index that I'm trying to sift up is self._parent, my helper function here, for the current index. And then what I'm going to do is I'm going to say while the parent index is not none, so I'm not reaching the top of the heap, and also, in addition to that, at the index, the key, so index 0, since we're passing tuples. Remember, when we insert key and value. So in order to compare the keys, I need to access the 0th element, so the index 0. If that value is less than the value of its parent, they should swap. So if I'm smaller in a min heap than my parent, I belong up and the parent belongs down. That is the rule of the heap. So heap parent index 0. If that is the case, so if I have a parent and this parent has a a larger value than me, we should swap positions. So I say self heap index and self heap parent index is the same as self heap parent index and self heap index. All right. And the index is then equal to the parent index, because what we need to do next is we need to move up and do the same thing. So if I swap positions with my parent, now I'm at the index that my parent was at, so I need to reset this and I need to calculate the next parent index. So the parent index is then self dot underscore parent index. And I continue to do that until I'm either no longer smaller than my parent or until I don't have a parent. And then I have the heap property restored. So now let us move on to the sift down operation. Here we need to do the opposite. So we are placed at the top of the heap. So we're assuming we are the smallest element in the heap, which is most likely wrong. And now we're going to find our way down by always replacing ourselves with the smallest child node that we find. So we're going to say here, let's remove this, while true. And what I want to do now is I want to find the smallest index. So it's either going to be me, then I don't have to change anything, or it's going to be one of my children. So either the left one or the right one. I need to know which one it is, and then I need to swap positions with this node. So I'm going to say here, the smallest, I'm going to assume by default I am the smallest. And then I'm going to say that my child is located at self.left index, and my right child is located at self._right index. And then I just need to make the comparison. So first of all, if I do actually have a child, so if actually left is not none, and the key value is actually smaller than the one I have, then I need to swap positions. So if self heap left 0, if that is less than self.heap smallest, which is by default my index, if that is smaller than that, then I need to go ahead and swap the position. So I need to say smallest is now considered to be left. I'm going to swap them in the end, but we're going to say now that the smallest one is located at the index that the left one is located at, and then I can just repeat the same thing for right, and it's going to also compare it to the left child, because if the left child is actually smaller than the parent, then it's also going to be stored in smallest. So I also do that comparison. If right is not none, self heap right 0 is smaller than smallest, then replace this by right. So at the end of this, we're going to always have the smallest variable pointing to the index, or having the index of the smallest node, of the node with the smallest key value. So I need to check if this node is myself. So if smallest is still index, it means that I didn't enter these if statements, which means that we're done. I don't have to change anything. So in this case, just break out of the loop. Otherwise, make the replacement. Heap index should be replaced with smallest. Like this. So we just swap the positions with the smallest element, and then we of course need to progress the index. The index is now smallest, and I repeat the process. So this is again the same idea that we had here. It's just the sifting down. I remove 32, which means 36 is now at the top because I take the last element, and now I sift it down. I look at left and right. Okay, this one is smaller, so I swap the position 36, 20. Then I look left, right. Okay, it's 25, so I swap this with 25, 36. So that is what we're doing here. All right, so that's actually it. Once we break out of the loop, the heap property is restored again, and the only two methods now that we need to implement are heapify and melt. Now, heapify again means we take a list of values, we take a collection of values, and we absorb them, we structure them as a heap, and we basically reorder them so that they fit the heap property. this can be done quite easily. What we need to do is we need to say self.heap is equal to list of elements in case we get any other collection format here. And then we're just going to reverse iterate. We're going to start from the last parent node and we're going to just sift down all the elements so that we restore the heap property in all the subheaps. And we do that from right to left. So basically from the bottom up, we sift down all the elements. Now the leaf nodes are already obviously trivially valid heaps because they are just a single node, but then we just go from right to left, from bottom to top, and we restore the heap property. So what we're going to do here is we're going to say for I in reversed range, and we're going to go to self underscore parent of a length self heap minus 1 plus 1. And the basic idea here is, again, we go to the last position, the last element that is part of the heap. We go to its parent, so that's going to be the last parent, because that's the first node where it makes sense to even sift down. And then we're just going to call sift down on all these indices. So self sift down I. There you go. And for the melt method now, all we need to do is we need to create a combined heap. So that's not the same as merging, by the way, because I think merging preserves the order. I'm not sure about this, but I think melding just basically throws them together and makes a heap. So the combined heap is going to be equal to self.heap plus other heap. And then we're just going to say self.heapify combined heap. So we're just using the method that we just defined. And one thing that you can optionally do, I think also with merging, what you do is you keep, I think you keep also the other heap existing. And in the case of melt, I think what you do is you say other heap.heap is now an empty list. So you basically really absorb the elements from the other heap. But I think you can implement this however you like, depending on what you want to do with that. So now let us talk about the runtime complexity. This is kind of interesting because we have different runtime complexities here. In a tree-based data structure, again, we're going to be working a lot with logarithms. So for the insertion, obviously we have a heap. In order to just add an element and sift it up, what do we need to do? Well, we do have a heap, and the heap is always going to be balanced. So we don't have anything like in a binary search tree where I can have some linked list-like structure. It doesn't work like that. I'm always going to have a balanced tree because I will never append something not to the next free slot. So I'm always going to have logarithmic time when I'm looking at the height. So in the case of a heap, the O of h is always O of log n. So this is different compared to the binary search tree where we could have imbalances and then we would have to go very long into a direction, and maybe in the worst case we have all of them lined up into one direction, so we have a linked list. In this case this can't happen, so what we need to do in the case of an insert is we just append at the end and then we just compare. We compare how many times height times in the worst case. Which means that the worst thing that can happen to me is I append a node at the very end, and then I have to shift it all the way up to the top, which would mean I have to go through all the levels, and the levels are logarithmic in terms of n. So the runtime complexity of insert is always O of log n. I mean, in the worst case, and not necessarily in the best case. In the best case, I just insert and it's fine, so done. But in the worst case, I have logarithmic runtime complexity. Now, peaking can be done in constant time because I just have to peak at the top element, done. Extracting does not work in constant time because we have the sift down operation. So this works again in logarithmic time. What's the worst thing that can happen? I take the last element at the top or to the top, and I have to sift it all the way down to the bottom. Worst case, logarithmic runtime complexity. Heapify, in this case, at least in our implementation here, is linear time because I have to go through all the elements. I mean, not exactly all. I don't consider the leaf nodes, but I have to go through all the elements and perform this. But also, each node is sifted down only once in the worst case. So I will not end up in a position where I have to do this worst case runtime complexity, which is, as we talked about, logarithmic in terms of n. I don't have to do this n times. So it's not going to be n log n, because in the worst case, I'm going to always have to only sift down every node once, because I'm going from back to front, which means that I won't have the case that I start at the top and go all the way down. This is not going to happen. So this is linear runtime complexity here. The melding also has a linear runtime complexity, because all I'm doing here is I'm adding the two lists together, and then I'm, heapifying, which has linear runtime complexity. This here can be done in constant time. Obviously, it's just a calculation. Same goes for left, same goes for right. And these, as we already talked about them, in the worst case are logarithmic. And because of that, also insert and delete are logarithmic, because I just have to remove. I can extract, of course, in constant time. I can also append in constant time. But the sifting up and down in the worst case can take logarithmic time runtime complexity. So I have to go through the full height, and the height is logarithmic base 2 in terms of n. So that is our implementation. Let's try it out to see if we have some mistakes. I think we always have some small typos or anything like this. So let's see if we have some problems here. For this, what I'm going to do now is I'm going to actually copy paste code that I already have. Because the good thing that we can do here is we can actually compare this with the heap in Python. So actually, this was the wrong key. Here now what I have is I have my min heap, and I heapify the following values: 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. I just have the same value as the key, doesn't really matter. And I then print what happens when I heapify that, and I compare that with the heapq package, or the heapq module in Python, which allows me to do the exact same thing. So if I run this now, I can see I get 1, 2, 3, or actually I get 1, 2, 4, 3, 6, 5, 8, 10, 7, 9. 1, 2, 4, 3, 6, 5, 8, 10, 7, 9. Exactly the same result as the heap package in Python. Only differences, I can also include here a package. So a payload, basically a value. And we can basically do the same thing now with the other methods. So I can compare here what happens when I extract the minimum. I can do the same thing with my heap package here, or with the heap module, using the heap pop method. So I can run this, and we get the same thing: 1, 2, 3, 1, 2, 3. And also I can insert new elements. So I can just, now I need to do this differently. There you go. So I can insert 2 and then print the heap. And there you go. I have, oh, sorry, I saw a mistake here in my parent calculation. It's actually index -1 divided by 2, not +1. This is why my code produced a problem now. So when I try this again, there you go. You can see 2, 4, 5, 6, 9, 10, 8, 7. It's good that we're always testing this, because these small mistakes are oftentimes something that's hard to notice while writing the code. And what I can do now as well, this is not something that I can necessarily compare with the heapq module, but what I can do is I can also melt 2 heaps. So I can basically say min heap 2 equals min heap, and then I can melt them together. And of course, I get a problem. Oh, I think I know what the problem is. I am inserting tuples here. They should be lists. No, this is not the problem. Combined heap is equal to self heap plus other heap. Oh, I think that it's self heap other heap dot heap. There you go. Now it works, and now we have these combined heaps in a single heap. So that is the idea of a heap. Again, this is how you implement a priority queue. You can use this now as a priority queue. You can schedule elements, and then the one with the highest priority, with the lowest value, with the highest rank, you could say, is going to be executed first or extracted first. And of course, you can reverse this. You can make this a max heap by just changing how it works. So you just call this peak max, extract max, and the only difference here is actually that you have to compare for being greater than and not for being less than, and you have to call this largest and not smallest. But the idea is the same. You just want to have the largest values at the top. It's just the other way around. But this is how you implement the heap data structure from scratch in Python. Alright, so we're going to implement the trie data structure from scratch in Python today, and as always I want to start by giving you guys a brief explanation of the data structure in theory here before we get into the coding. And as a side note, for those of you who are interested in that, the data structure name is written like this, T-R-I-E, and it actually comes from the word retrieval, which means that the original correct pronunciation would be tree. Now, why do we call it trie? Mainly to distinguish it from the concept of a tree, especially because the trie is also a tree. It's a tree data structure, which means that if you just say, oh, we're working with a tree, we don't really know what we're talking about. If I say I'm working with a tree data structure, so we're calling it trie mainly to distinguish it from the tree, to know it's not just a tree, it's a trie. That's the only reason why we pronounce it that way. Actually, it would be pronounced tree because it comes from the word retrieval. Just as a side note here for those of you interested in that. But let's take a look at the data structure itself. What's the idea behind it? It's a tree, as we said, and it's very useful for working with strings and primarily used for things like auto-completion or having a dictionary, for example. And the idea is the following. We have a root node, and every node has two things: a dictionary of children or of child nodes, and a flag saying if this is the end of a word, yes or no. So we're going to say that if a node is the end of a word, we're going to write end in it. Otherwise, I'm going to leave it empty. So this is the root node now. It is not the end of a word, and our trie is empty. Now, let's say I want to insert a word, for example, hello. How would I do this? Now, what happens here is I go letter by letter, and I insert the word into this trie data structure. So right now, the root node doesn't have any child elements. So what I do is I'm looking for H. H doesn't exist, so I'm going to create a new key value pair where H is the key and H points to a node. And this node now has, again, its own dictionary and can be the end of a word or not. Now, it's not the end of a word, so we're going to continue. Next up, we have E. E is not part of this node or of this dictionary, so we're going to add it. E points to the next node, which again has a dictionary. Here we're going to do the same thing. L points to the next node, has a dictionary with another L, points to the next node, and this one has a dictionary with O. And then this O points to a node which has an empty dictionary and is the end of a word. This is how we would insert hello into our trie. So we have the root node with the dictionary. The H points to a node that has an E, pointing to a node that has an L, pointing to a node that has an L, pointing to a node that has an O, pointing to a node that right now is empty and has end, the end flag set to true. Now, we can also import or insert another word, for example, minimum, like this, minimum. And we could see what happens here. Now, there's a reason I choose this word. I'm going to show this here in a second. But let's say, now I'm not going to use the dictionary notation here. I'm just going to use connections, but it's the same idea. The M is pointing to a node, which is pointing to, which has I pointing to another node. N, I, M, U, M, and end. So why am I using this word? Because there are a couple of words that are quite similar, and we're going to see what happens, for example, if I now insert the word minimal, like this, minimal. What happens in this case is if I want to insert this word, I go M, I, N, I, M, and then I see that here in this dictionary, this node here has the dictionary U that points to this node. And what I do now is I add another key value pair. So I say A, which points now to another node. I'm going to do it like this. So I'm going to just say we have another branch here, A, which goes to another node, which goes using L to another node, which is also the end of a word. And now you can see they have the same prefix. By the way, this data structure here is not just called trie, it's also called a prefix tree. This is also a way to refer to this data structure, a prefix tree. And the reason for that is you can see M-I-N-I-M, minim, is the prefix for minimal and for minimum, which can be useful again for auto-completion. Now, another thing that we can do is, let's say I want to insert the word mini. What happens in this case? Well, in this case, all I have to do is I have to go M-I-N-I, and then I have to set this to end. Now, end doesn't prevent my try from going further, so I can still go to minimal, but it says that this is the end of a word. It doesn't have to be the end of the search, but it is the end of one word, so mini is actually a word. And this can be useful now because if now I ask, okay, give me an auto-completion for MI, I can efficiently find mini, minimal, and minimum. And I can extend this, I can build a dictionary like this, I can have certain keywords like this. This is a very useful data structure, and this is what we're going to implement in Python from scratch today. So let us get started. I'm already in my current directory. I'm gonna delete everything that's in here. Actually, we don't have anything in here. So I'm gonna create a new file. I'm gonna call it trie.py. And we're going to have, of course, a node class. So class node is going to have a constructor, and it's going to have self.children set to an empty dictionary, and or actually I'm not sure if this is an empty dictionary or a set, so let's actually say dict like this, and then we're gonna say end of word, or actually let's call this is end of word is equal to false by default. That is our node. That's about it. And then we're going to have a class trie. And this trie is going to have an init method. And in this init method, we're going to initialize the root node. So we're going to say self.root is equal to node. All right. So every tree is going to start with a root node that has an empty child dictionary and is not the end of a word by default. Now, let's define again what kind of methods we're going to implement for this data structure. We're going to have an insert method, which is going to allow us to insert a word into the trie. We're going to have a search method, which is going to tell us if a given word is part of the trie. So, for example, in our tree here, if I type mini, I'm going to get true. If I type minimalistic, I'm not going to get a true. I'm going to get a false. That's the basic idea here. Then we also want to have a delete method so that I can remove words. How would I do that in theory? Of course, I would just remove the end flag if I remove mini, for example. So if I remove mini, I would just set this to false again. If I remove something else, I also delete the nodes and the connections. We're going to take a look at that when we get to the implementation. Then we also want to have has prefix. The basic idea here is that we check if the prefix is part of the tree or not. And then we also want to have two a little bit more, not necessarily complicated, but they're going to take more, they're going to have a higher runtime complexity, if that's the correct term, higher. But they're going to be a little bit more difficult, which are going to be the starts with method. So for this method, we're going to pass a prefix, and this prefix, or this method, will give us all the words that start with this prefix. So it's going to search the tree. And then we're going to also have list words, which is basically going to give us all the words of the dictionary, you could say. So we don't need a prefix for this. We just get all the words. And that's basically it. That is going to be our trie data structure. Now let us start with the insertion. We already talked about this. How do we insert? We start at the root node. We say current node is equal to root. And then what we do is we say for character in our word. So we go character by character. We say if the character is not part of the dictionary of the current node, so if we don't find the character as a key in the children dictionary of the current node, what we do is we say current node dot children, add this new add this character as a key and let it point to a new node that we create. And whether we had to create it or not, afterwards we're just going to say that the current node is going to be that node. So current node dot children C. So either it was there before, then we're just going there, and otherwise we're creating it and then going there. And we do that until we have no characters left in our word, and then what we do is we say current node dot is end of word equals to true. It's as simple as that. We just follow the path until we get there, or we have to create new nodes until we get there, until the word is processed, and at the end, at the node that we're currently at, we're going to just set end of word to true. This can be an already existing node, like it was the case for mini. In this case, we just set it, or it was the node we just created. In this case, we also just set it. So the insertion is quite simple. We're going to talk about the runtime complexities later on. The search is also quite simple because we have to do basically the same thing, but instead of creating it, if we don't find it, we return false. So we say current node is equal to self.root, and then we say for character in word. If the character is not in the current node children, we're going to return false because we obviously don't have it. So if I get to a point where I have a character and it's not part of the children dictionary of my current node, it means the word does not exist, obviously, because the next character does not exist. So I'm going to return false in this case. Otherwise, I'm going to keep going down the line. So I'm going to say current node children C, move further. And in the end, we're going to say once the word is processed, we want to know the word or the node I'm currently at. Is it the end of a word or not? So I'm going to return current node is end of word. Because of course I can find the term. For example, here what I could find is minimum without the M, so minima. Like here, I could end up here, which would be a valid node, but I would not have it set to end, which means that I would get false here as a return. So that's that. Now, the rest is going to be a little bit more, or actually has prefix is kind of simple. So for has prefix, we can also do the same thing. Actually, I think we can just copy this. Actually, now I copied it to my to my clipboard. So let's go paste it down here. The only difference here is that we're going to return true every time. So it doesn't need to be the end of the word because we're not checking if the word exists. We're checking if the prefix exists. So if I end up at a node, I can return true. Now, the deletion will be a little bit more complicated because we need to define a helper function underscore delete. We're going to say def underscore delete. And this function will get parameters so that we can keep track of certain things. First of all, it will get the current node. It will get the word, and it will get the index so that we can recursively call it and update the progress, so to say. The idea is I'm going to call this function or this method in delete once initially, so self-delete on the root node. So I'm going to say self.root, this is the word that needs to be deleted, and I'm currently at index 0. So we haven't processed anything of the word yet. And in our delete method, this is going to be a recursive method, so it's going to call itself. We're going to have, first of all, some base cases for terminating. We're going to say if the index is equal to the length of the word, then we're done. And I basically just have to see, is this the end of a word? So if this is not, the current node is not the end of the word, we return false. Why do we return false? Because we don't need to do anything. We don't need to delete anything. This happens when the word didn't exist anyway. So we don't need to delete anything on the upper levels. We can just say, okay, if I'm ending up at a place that is not a word, I don't even have to do anything. So return false. The return value is important because we have to also recursively remove nodes if it's necessary. So basically, if I'm removing this here, I just need to set it to not end of a word anymore. So if I'm removing many. If I'm removing minimal, I have to remove this, I have to remove this, and also this connection here. So I have to remove more than just setting this to not being an end anymore. Unless I want to keep like this, or not even unless I want to keep the structure, I have to delete it because otherwise minimal would be a valid prefix, which it shouldn't be. So this is why I use the return values here. So if I end up at a place that is not the word, I just return false because obviously I'm not removing anything here. And then I'm going to say current node, in all cases, current node is end of word is going to be equal to false. Now, if it was false already, this doesn't change anything. If it was true, it means that I'm ending up at a place where this is a word, this is the end of a word, and it is set to true. So I'm going to set it to false now to say this is no longer a word. I'm removing it from the dictionary, so to say, from the trie. And then I want to return here length of current node dot children is equal to 0. If that is the case, I want to return true. So if I don't have any child nodes at the current node, I can return true because that means I can delete other nodes as well. Whereas if this has child nodes, I cannot just delete everything because there are other words that would be impacted by it. So I return true, which means you can delete the node if this node doesn't contain any child nodes. So that's the base case. Otherwise, what we're going to do, or not just otherwise, or actually otherwise, yeah, because we return if we get to the if statement. Otherwise, what we're going to do is we're going to say the character is the word at the specific index. Remember, we're passing the index here, or we're going to pass the index here recursively when we call the delete method, but by default or in the beginning it's 0. So we're getting the first character or the character at the index. And then we say node is equal to current node children get C. So from the current node, I'm looking at the child dictionary. I'm getting the node that corresponds to the key C. Now, there is the case that this node does not exist. So if, or this key does not exist. If this is the case, this is going to return none, and I can return false because the word doesn't exist. If the word does exist, what I do is I delete the current node. How do I do that? Or I don't delete the current node. I call recursively the delete function, but I have to store whether I have to delete the current node or not in a variable. So this is why we need to return values. So we say delete current node, you could imagine a question mark here, is equal to self._delete, calling it on this next node with the same word and the index increased by 1. So what this means is we go one node forward and we also increase the index by 1 so that we can continue the same process down the line. And this is going to recursively return true or false. And if it returns true, it means that I can delete the current node. If it returns false, it means that I'm not going to delete the current node. So at some point, this is going to return finally, and then I want to know if delete current node. What I'm going to do is I'm going to delete current node children C, and I'm going to return also here for this node if the length of the current node dot children is equal to 0, and also the current node is not end of the word. So basically, I get the instruction delete this node, and then I delete this node from the children, and I also say for this node delete it if it has no children, or if it's not the end of a word, so that we can recursively delete all the nodes that are no longer necessary in our trie. I hope this was not too confusing in the explanation. The basic idea here visually, again, let me show this, is for some nodes, when you want to delete the word, like mini, all you have to do is you have to delete the flag that it's the end of a word. You don't have to remove any other references here because it has child nodes. But for example, if I remove minimal, this doesn't have child nodes. So I can remove this node. I can remove, of course, the flag. I can remove that this is the end of a word. but I also don't have children, which means I can remove this node. Which means I can remove this node because it then also doesn't have any children anymore, which means that this connection can also be removed. But then, of course, this should not be removed because it does have children. It does have minimum. Another word that is also part of our trie. So I hope this is somewhat easy to understand here why we're doing it that way. Even though the recursion might be confusing, but we're basically returning, should you delete me or should you not delete me? That's the return value. All right, so that's the delete method. And now for the starts with and for the list words method, we're going to use a depth first search, so a DFS algorithm. The basic idea is you want to go to a certain prefix and then you want to get all the child words, so not just the nodes, but the words. You want to explore all the child nodes to find words and you want to collect them in a list. So we're going to say words is equal to an empty list, and we start again at the root node. And then we say for C in prefix. So we want to go to the position, and we want to say if C not in current node dot children, we're going to return an empty list, or actually we can return words because it's going to be an empty list at this point. But if we don't get into this if statement, we're going to just go further and further. We're going to say current node is equal to current node children C, which means we're going to go to the prefix. For example, if my prefix is M, or if my prefix is mini, or let's say min, I would go to this point here, min. This is where I'm at now. And from here, I can start a DFS. So I can go like this and then like this. So a depth first search. All right, so once this is done, we're going to be at the position of the last prefix character, and then we're going to define here a helper method, which is going to be it's going to be a nested method inside of this starts with method, and I'm going to say underscore DFS is going to get a current node and a path. The path is important to be able to reconstruct the word, and this is going to recursively call itself. So we have quite a bit of recursion today. Basically, the idea is if the current node is the end of a word, we want to store it. We want to add it to our words list here. So if we end up at a node that is the end of a word, what we want to do is we want to say append to the words list the path. And the path is going to be a collection of characters. So in order to get it as a word, we need to join it. So we're going to say join, not word, sorry, path. So the path is going to be what we recursively pass here to the function call. So if we are at the end of the word, get all the characters, join them together, and append them to the words list. And then we're going to say for C child nodes in current node children items. So basically for the key and child node, C being the character that performs the transition, child node being the node that the transition is performed to, we're going to say DFS, go to that child node and say path plus and then list C. This is important that it's a list because we're extending an existing list. So this is the list of characters that we have. We collect all the characters, and at the moment we arrive, or the moment we arrive at the end of a word, we collect it. And of course, we need to call this method once. We need to say DFS current node here, and we start with a prefix. This is important because you want to not start with an empty list. You already have the beginning. For example, min is already part of the word, so you want to append to it. In our example, I can show you that. What we want to do here is we want to go to this position, to min, and then what we want to do is we want to do the DFS. So we want to go down. Oh, here's the end of a word. So what I do is I have now M-I-N-I, and I want to join them together to mini and collect them in my list of words. Then I go deeper. I say M, then I say A, L, O. End of word. Perfect. So I can say now I have M, A, L, join them together, minimal. And then I also have here a second call, of course, U, M, O, end of the word. Okay, this is minimum. So I found all the words that have this prefix, that start with min. And of course, what I need to do in the end is I need to return the list of words. All right. Now, list words is basically a similar approach, only difference being we don't need a prefix. So what we do here is we say words is equal to an empty list. And we say, again, DFS. We're going to have a current node and a path. Actually, I think this is the exact same implementation. So I'm going to just copy this. And we're going to say that the only difference is that we're calling this DFS now on self.root with an empty list as the prefix. And then we say return words. That's it. Now, if I didn't make any mistakes, which would be surprising as always, that is the trie data structure. So I'm going to write some test cases here just to see if this works. And then we're going to talk about the runtime complexity. So if name is equal to main, what I want to do is I want to create a trie. And actually, let me think about this. I'm going to just copy paste what I have here in my prepared code, so that we don't have to, actually this was not the correct key. Let me just do it like this, there you go. And what we do here is we have basically a trie, we insert hello, Henry, Mike, minimal, minimum. Let's also insert many. And then we have, or actually I'm inserting mini down here, so let's remove it here. Let's run this code to see if it works. No, it doesn't work. Key error H, perfect. This means that our insert method probably doesn't work correctly. So what's the problem here? Oh, I found the problem. It's that we're missing a not here. Of course, you want to create a new node if it's not in the children. You otherwise want to just go to the node. But if you don't have the character already in the list, then you want to create a new one. Otherwise, just jump to the existing one. That's the problem. We have another problem, which is name word is not defined. So where is that again? This is in has prefix. Oh, is this because we're lacking a parameter? No, actually has prefix is fine, but we need to say prefix. And now it should work. Okay, let's compare the code, or let's compare what it should do. We insert hello, Henry, Mike, minimal, minimum. We can print that, we get it. This is from list words, so this works. Then we say has prefix. Actually, what we're asking for here is mi. It has it. If I say starts with mi, I get Mike, minimal, minimum. If I say delete minimal, and then I do starts with mi again, I get Mike and minimum. Then I search for certain words. I search for minimum, minimal, and mini. I get, in this case, true, false, false, because I removed minimum. And then we insert, or I removed minimal. Then we insert mini, and then I say starts with mi, and I'm getting Mike, mini, and minimum. So as you can see, this works. And now let's talk about the runtime complexity. How difficult is it to do that? Well, for the insert, we have O of m, so linear runtime complexity, where m is the length of the key. So actually the length of the word, we could say. So depending on how long the word is that we're inserting, that's what determines the runtime complexity. It doesn't matter how large the tree is. It doesn't matter, you know, how many words are already in there. It matters how long the new word is that I'm trying to insert. O of m, where m is the length of the word. So it's linear in terms of word length. When it comes to the search, it is basically the same. O of m. Actually, let me just copy that. Because what do we need to do? We need to just go and look up the characters and go to the next node, and next node, and next node. Now, of course, we can terminate earlier if we see that the first letter is already not part of the trie. Then we can, of course, just terminate. But in the worst case, we have O of m, which is the length of the word itself. So then the same is also true for deletion. O of m in this case. Actually, I wanted to paste this here again. And for has prefix, we also have O of M, but for the other one, for the starts with and for list words, we have different runtime complexities. For starts with, we have the following. We have O of M plus K, where M is the prefix length and K is the total number of characters in all suffixes. Basic idea being I definitely have to go M because I have to go to the note where the prefix ends, so that's for sure. And then I have to go to all the characters in all the suffixes. So for example, in our tree, in our trie here, we definitely have to go to min, but then I also have to go to IMAL, MUM. Now, the thing is, if they overlap, I can save certain things. So for example, if my prefix is M, then I, N, I, and M overlap. So I only have to count them once. So I don't actually have to count all the words lengths, because then I would have I, N, I, which would be 3. I would have I, N, I, M, A, L, which would be all of that. And then I would add all of these together. If I have overlaps, this results in much less characters that I have to count, because if they only differ in the last couple of characters and I have huge words, that's going to make a difference. But in the worst case, I have O of M plus K, where M is the prefix length. That's how far I have to go for sure. And then K depends on the overlaps, but K would be the total number of characters in all suffixes. And then we have also list words, which is easy to denote. It's just O of N, but N is the number of notes in the trie. We have to go through every single note in order to list all the words. So depending on how many notes you have in the trie, that's how many notes you have to traverse in order to list all the words. So yeah, this is how you implement the trie data structure in Python from scratch. Alright, so we're going to implement the graph data structure from scratch in Python today, and I think most of you guys will probably already know what a graph is. Nevertheless, I want to give you a brief theoretical explanation, just so we know what we're talking about. A graph basically consists of a bunch of nodes and a bunch of edges. So we have nodes like these here. Usually they have some label assigned to them, like A, B, C, or 1, 2, 3, and so on. So let's call them 1, 2, 3, 4, 5, 6, 7, 8, 9. And these nodes can be connected by edges. So 1 and 2 might have an edge, 2 and 3 might have an edge, 3 and 4, 5 and 6, 7 and 6, maybe also 3 and 6, maybe 8 and 6, 6 and 9, 8 and 9, 5 and 8, 4 and 7, 4 and 3, 4 and 6, maybe also 1 and 5, and also 1 and 4, whatever. That would be a graph. And also, one thing that you might notice is that a tree is also a graph with a specific limitation, that there are no cycles. So for example, if I have something like this, A, B, C, and then maybe D, it doesn't have to be a binary tree, it can also be something like this. This is a graph, but this is also a tree. But the moment I create a cycle like this, it's no longer a tree, but it's still a graph. And what we're seeing here is an undirected graph. So it means that the connections go both ways. 1 is connected to 2, 2 is connected to 1, and unless I specify that I want to have a directed graph, every connection goes both ways. Now, in a directed graph, every connection needs to have a direction. So 1 goes to 2, for example, but 2 doesn't go necessarily to 1. If I also want to have 2 go to 1, I need to add a second connection from 2 to 1. So that's possible, but then I need 2 connections. And every single connection has to have a direction. So we cannot have undirected and directed connections in the same graph. It's either a undirected graph or a directed graph. So that's the basic idea here. And also we can have weighted graphs. So it doesn't have to be just directed, undirected. Both can also be weighted graphs, which means that each connection has a certain weight to it. This can be a cost, this can be a speed, this can be a reward or something like this, depending on what you're trying to model. But for example, one question could be, what's the fastest road from, or the fastest path, the shortest path from 1 to 5, for example. And if this connection here doesn't have a weight, if none of the connections have weights, then of course that's the shortest path. I just have to hop once. But if I assign weights to the connections, like costs to the connections or slowdowns, I could say that this has a cost of 100. And maybe I could say this one has a cost of 50. And this one has a cost of 10. And then this one has a cost of 10 as well. Then this path already would be faster because it only costs 70 or cheaper, whatever you want to call it. But then maybe I have connections like these, 1, 1, 1, 1, 1. Then of course that's the cheapest path possible, even though I have to go through a lot of nodes. But if they're all cheap paths, I can just go like this, and that's the fastest or cheapest way to 5. So depending on whether we're working with weighted or not weighted graphs, this changes what we're looking for. Now, graphs are very versatile. They have a lot of different use cases. They're used all over the place for network analysis, for also graph neural networks, and a lot of different things can be done with graphs. But in this video today, I don't want to show you every single thing that you can do with graphs. I just want to provide a basic implementation, adding nodes, removing nodes, adding edges, removing edges. And I want to also show you some basic stuff like DFS and BFS. So BFS stands for breadth first search. We're going to talk about this in more detail when we get to the implementation. And DFS, which is depth first search. These are two things that I want to show you. Then I'm also going to provide you with the code for Dijkstra. I want to also provide you with the code for transforming the adjacency list to an adjacency matrix. And I also want to provide you with code for the shortest path algorithm, but I'm not going to explain them, so I'm just going to copy paste them. I'm going to upload them to GitHub, but these two here I'm going to actually implement with you guys in the video. I just don't want to make this video too comprehensive because we could implement a ton of things when it comes to graphs. I want to give you a basic implementation, and then you can take it from there and extend the functionality if you want to. So that's what a graph is basically. So let's get into the coding. We're going to open up a new Python file here. I'm going to call it graph.py. And this time we're only going to have the graph class. We're not going to have any node class here, even though we're going to have a bunch of nodes, but they're going to be represented as an adjacency list. Maybe that's one thing that I want to show you as well also here in the theoretical part. An adjacency list is basically how you can represent a graph. So for example, this graph could be represented the following way. I would have the adjacency list that 1 has a connection to 2, 4, and 5. And then 2 would have a connection to 1 and 3. And then 3 would have a connection to 2, 4, 5, 6. Like this. That would be an adjacency list. Adjacency list. We can also have an adjacency matrix, which makes more sense or can be more interesting when we have directed graphs. But basically an adjacency matrix, the idea here is that I have all the nodes, 1, 2, 3, and so on. 1, 2, 3, and so on. And I basically say, do I have a connection from 1 to 2? If I have one, yes. Do I have one from 1 to 3? If I have none, 0. And I fill this up with ones and zeros. So that's just a different way to represent this. We're going to work with the adjacency list, and we're going to start now by saying class graph, and we're going to define the init method. We're going to pass the argument directed. By default, this is going to be false, so it's going to be an undirected graph by default. And we're going to set directed equal to directed. Also, we want to initialize an empty adjacency list. So we want to say self.adjacency list is equal to dictionary, to an empty dictionary. And then we want to define all the methods that we're going to implement. Now we're going to need a representation dunder. So repr self, this is just going to print the adjacency list. We're going to have an add node function or method where we're going to pass a node that is going to be added to the graph. We're going to have add or actually remove node as well. We're going to have add edge, which is going to take as parameters from node to node, and weight. By default, weight is going to be none. This is going to allow for weighted connections, which are optional. You can also have not weighted connections. We're going to have remove edge, which is going to also take from node and to node as parameter. Then we're going to have get neighbors for a given node. Also not too difficult to implement. We're going to have has node, which is also going to be very simple and straightforward. We're going to have also has edge from node to node. Then we're going to have get nodes. And we're going to have get edges. Now, besides that, we're going to have the two functions or methods that I talked about, which are the BFS and the DFS. So we're going to say BFS self starting from a specific node, from a start node, and also the same for the DFS. All right, so these are the methods that we're going to implement in this video today, and I want to start right away with the representation dunder. All we're going to do here is we're going to create a graph string, and it's going to be an empty string in the beginning, and then we're going to iterate over the pairs in the adjacency list, and we're just going to display them with simple arrows. So we're going to say here for node and neighbors in adjacency list, self.adjacency list actually, we're going to just do the following to the graph string. We're going to add the following, an f string, which is going to be the node and an arrow pointing to all the neighbors, and then also \n so that we have a new line, and then we're going to return that. So that's basically the graph string. Now, adding a node is also quite easy. We're going to just say if the node not in adjacency list dot keys, or actually we don't need to do dot keys, we can just do it like this. If it's not already in the adjacency list, we're going to say self.adjacency list node is going to be equal to an empty set. So we don't have any neighbors yet, we just added the node. Otherwise, we're going to raise a value arrow. We're going to say node exists already, or you can just do nothing. Depends on what you want to do. So that's that. Now, removing a node is also quite simple. If the node is not in self.adjacency list, then we're going to say raise value error node does not exist. So you're trying to remove something that does not exist. Otherwise, for every neighbor in self.adjacency list dot values, remove that node. So we're going to say for every set of neighbors, if this node occurs there, remove it from there because it no longer exists. So we're going to say neighbors.discard node. And then we're going to, of course, also say delete from the adjacency list this node entry. All right, so that's that. For adding an edge, we have to consider that we could have a weighted connection or we could have a not weighted connection. So we're going to say, first of all, from nodes, if the from node is not in self.adjacency list, what we want to do is we want to create it. So we want to allow for edges to be created for nodes that don't exist yet, not because this is possible, but because we're just going to add the nodes on demand. So we're going to say here, if from nodes is not in self.adjacency list, we want to say self.add add nodes from nodes. This just makes it easier. We don't have to create the nodes manually and then the connections. We can just say add the connection from 1 to 2, and if both don't exist, we're going to create them. So we're going to do it like this. I'm going to copy that. We're going to do the same thing for the 2 nodes. And then we're going to say if weight is none. So if we don't have a weight, we're going to just say self.adjacency list 2 nodes is going to be, or actually from node first, from nodes 2 nodes. And then we're going to say if this is a directed graph, we want to have it only in one direction. Otherwise, so if this is not a directed, so if self-directed, or actually if not self-directed, we also want to do it the other way around. Adjacency list 2 nodes add from node. So then it goes both ways. A connection between 1 and 2 is also a connection between 2 and 1 if it's not a directed graph. And otherwise, if it is a weighted graph, we don't want to just append the node, we also want to append the weight. So we actually want to take this, copy it, paste it down here, and the only difference is that now we add a tuple, and the tuple is going to be 2 nodes weight, and it's going to be, oh, now I pressed the wrong key, it's going to be from nodes weight. And that should be it. So that's how we add an edge, and then we're going to also remove an edge. How do we do that? Well, if from node is in self adjacency list, and if to node is in self dot adjacency list from node, so if the node exists in the list and if actually the to node is a connection, is a neighbor of from node, then we're going to just say self dot adjacency list, and then from node, from here we want to remove the to nodes entry, actually parentheses. So that is a case where everything exists and everything is fine. Otherwise, we want to say here again, raise a value error. Actually, I just called this remove. It's remove edge. This will be just edge does not exist. The edge that we're trying to remove does not exist. Otherwise, here we can even say node does not exist. So raise value error. Or actually, let's just say edge does not exist. It's simpler. I don't want to explain all the details of why it didn't work. But inside of here, we also want to do something else. We want to say if not self-directed, we also want to do it the other way around. So if I remove an edge, I have to remove it from both entries unless it is a directed graph. So I'm going to say here if from node in self.adjacency list to node, if that's the case, self.adjacency list to node remove from node. All right, so that's the removal of the edge. The other functions here now, except for BFS and DFS, are very easy to understand. Get neighbors, obviously all we have to do is we have to return self.adjacency list, adjacency list, and then get the specific node. In the default case, just return an empty set. That's it. Get all the neighbors. Empty set by default if it doesn't exist. Has node is also quite simple. Return node in self.adjacency list. That's all we need to do for this. Has edge is also just return, or actually we need to say if from node in self.adjacency list. Then we need to say return to nodes in self.adjacency list from node. So is it part of it or not? This is going to return a Boolean, and otherwise we return false anyways. Get nodes is also not too difficult. Just return a list of self adjacency list dot keys. And the edges are actually just a simple loop, or actually two loops. We're going to say edges is an empty list for from node neighbors in self dot adjacency list dot items. So we iterate over the items in the adjacency list, and then we say for two nodes in neighbors edges append, and then from node to node. So this is all very simple. Now, I wouldn't say difficulty, but the interesting stuff happens now in BFS and DFS. So what's interesting about these two functions or these two algorithms is that we're going to use data structures that we've already talked about in this tutorial series. We're going to use a queue for the BFS and we're going to use a stack for the DFS because of the different order or the different processing order. In a queue, it's first in, first out FIFO, and in a stack, it's last in, first out. And because of that, we have these as helping data structures here. In this case, we're just going to use lists and we're going to pop the elements in different ways, but these are basically queues and stacks. So we're going to say here for the BFS, we want to have a set of visited nodes, and we want to have also a queue of nodes to be processed. We are going to start with a single node in here, and then we're going to have our resulting order, which is going to be the traversal order. And what I want to do here is I want to say, while we still have elements in the queue, we want to get the next element to be processed in the first in, first out way. So we're going to say here that the node is going to be queue.pop at index 0 to get the first element. The first element was added to the queue. And then we're going to say if this node is not already in visited, so it's not already processed, we're going to go further. So we're going to say, first of all, add it to the visited nodes, and then also append it to the order, so to our resulting list. And then I want to get all the neighbors of this node. So in the beginning, all the neighbors of the starting node. So we're going to say neighbors is equal to self.adjacency list, and or actually we have a function for this, right? Get neighbors. So we're actually going to use the get neighbors function. Self.get neighbors for this node. And what we want to do now is we want to iterate over them. We're going to say for neighbor in neighbors, if is instance neighbor tuple, which means that it's a weighted connection because we have a weight. We don't just have the individual value, but we have also the weight. What we're interested in then is just the value because we don't care about the weight now. We're just going to say neighbor 0. Otherwise, we're just going to take the neighbor itself and we're going to say q dot, or actually, sorry, not otherwise. We need to do this in all cases. The only case in which we don't do that is if we have already visited that neighbor. So if neighbor is not in visited, we're going to append it to the queue. So we take a look at all the neighbors that we have. Have we already processed them? Have we already visited them? If not, put them to the queue and process them further again in this first in, first out principle. And in the end, this is going to result in the BFS traversal order because we're taking in the neighbors, and since they're the first elements to be added, they're also the first elements to be processed, which is the BFS approach of going layer by layer. In the DFS, we're going to do all of that the opposite way. We're going to do that with a stack, and we're going to change queue to stack. And besides that, I think the only thing we're going to change is, of course, we're going to do pop without an index. So it's going to be the last element. And we're also going to sort the neighbors. So we're going to say for neighbor in sorted neighbors, and we're going to reverse the order. Now, I think that's not necessary, but that's usually what you do. So just reverse the order of of the neighbors when you list them. But besides that, this is actually the same. The only difference is I'm going last in, first out. So whatever enters first is processed last, which is the depth first approach. This is why we use a queue and a stack. So before we go to the other functions that I have here, or actually I'm going to go through the other functions, I'm actually just going to add them here to show them to you. The reason I add them is because they have functionality that interacts with the weights, but I'm not going to implement it. I'm not going to explain it here. I'm going to provide the code to the GitHub repository, or in the GitHub repository for this tutorial series. But if you are interested, for example, in the explanation of Dijkstra, I have a video for this, or on this channel. In my algorithms and data structures tutorial series, you can take a look at the theory there. But this is the implementation here. It uses a heap, and we also have shortest path here. And also I want to use a method called toAdjacency matrix, which is going to allow us to turn our adjacency list into an adjacency matrix. So I'm going to also paste this here. Actually, this needs to be one level before. So again, these are not going to be explained. I'm just going to paste them here, and you can copy paste them from the repository. But now we want to see if our graph actually works. And for this, I'm also going to copy paste the examples here. So I already have the main section. Basically, we create a graph A, B, C, D, E, F, G. Actually, this is not even necessary because we can just create the edges. And then I'm trying to find the shortest path from A to C. Now, just so we know what we're talking about here, let's actually try to recreate this graph visually. So what does this graph look like? We have A. This is a weighted graph right now. We have A points to B, A points to C, B points to C as well. So here we have a cost of 1, here we have a cost of 10, here we have a cost of 1, then we have B going to D, D going to C as well, all with a cost of 1. We have A going to E, we have E going to F, we have G going to F. I think this is an undirected graph, so it doesn't really matter. We have F going to H, and we have H going to I, and we have I going to G, which is now this, and this one has a connection of 100, or a cost of 100, and all these have 1. So that is our graph, and we're asking the following: BFS from A, DFS from A, Dijkstra from A, and then shortest path from A to C. Let's run this. Okay, I'm calling this method EGDE and not etch, so add etch. And also I have a problem here. I need to actually iterate over the items of the adjacency list, not over the adjacency list keys. So that should be it. Let's run this. And we also have a problem. Did you mean node? This is 86 in BFS. So let's go 86 in BFS. Yeah, actually, of course, node, not nodes. Also here, node, not node R. Have some typos in here. And Q is not defined, obviously, because we're working with a stack here. So stack.append. But besides that, we also have it. We also have it here, of course. Stack. And that's it. Okay. So let's take a look at that. What do we have here? We asked for, what did we ask for? We asked for the adjacency matrix, which is what we get here. With the connection weights, we asked for the BFS from A. So we get AEC, which makes sense. So AECB, because these are the neighbors. Then we get FD, which are the neighbors of the neighbors. And then we get the rest, which is HIG. In case of DFS, we get A, B, C, D, E. So A, B, C, D. Okay, then it goes to the next neighbor, E, and then we get to F, and then it goes H, I, G. also makes sense. Then the Dijkstra is, in order to get from A to A, we need 0 cost. In order to get from A to B, we need 1 cost. In order to get from A to C, we need a cost of 2. In order to go from A to D, we need a cost of 2, and so on. So you can just see the cost for every shortest path. And then the shortest path from A to C is A, B, C, which is of course true because A, B, C has a cost of 2 and AC would have a cost of 10. All right, so this is how you can implement the graph data structure from scratch in Python.